Welcome to the CCAK exam preparation course, where we will bridge the gap between traditional audit rigor and the complexities of modern cloud environments. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to ISACA or the Cloud Security Alliance, CSA, in any way. All trademarks, including CCAK, belong to their respective owners. This content is for informational and educational purposes only and does not constitute professional legal, audit, or compliance advice. Always consult with a qualified professional or the official certifying body before making business or certification decisions. In this opening chapter, we provide a comprehensive roadmap for mastering the Certificate of Cloud Auditing knowledge, designed to ensure you possess the technical, operational, and administrative expertise required to pass the exam and excel in your professional role. By navigating this syllabus, you will gain a deep understanding of ISACA and CSA frameworks while learning how to evaluate cloud security controls with precision and independence. Our methodology focuses on the practical application of audit principles within distributed systems, moving beyond theoretical knowledge to cover critical areas like the shared responsibility model, risk mitigation, and compliance validation. You will explore how to audit vendor-independent attestation reports, assess cryptographic implementations, and maintain oversight in dynamic, virtualized environments. We emphasize the necessity of aligning business strategy with IT security to ensure resilience across hybrid and multi-cloud architectures. Throughout this journey, you will learn to evaluate the effectiveness of controls through the lens of continuous auditing and vulnerability management. We will dissect the nuances of incident response, forensics, and identity management, ensuring you can identify deficiencies and track remediation efforts effectively. This instruction is tailored for those who need to demonstrate competence in auditing complex microservices and container workloads, while also ensuring data sovereignty and regulatory compliance. By the end of this program, you will be well-equipped to apply automated assessment tools and traditional auditing wisdom to the rapidly evolving cloud landscape. This course is essentially your definitive guide to professional credibility, helping you master the interplay between provider responsibilities and tenant obligations. If you are serious about advancing your career and proving your ability to secure the cloud, this is the environment where you will sharpen those exact skills. I look forward to guiding you through this material. Welcome to the foundation of our course, where we dive into the NIST cloud definitions to master the baseline vocabulary of cloud auditing. This chapter provides the essential framework for all subsequent modules, ensuring you possess the precise definitions required for the CCAK exam. To audit cloud environments effectively, one must first possess a rigorous, unambiguous understanding of the NIST SP 800-145 definition of cloud computing. This document is not merely a set of guidelines, but the foundational vocabulary for the entire industry. When we evaluate whether a service under audit truly functions as a cloud service, we look for 5 specific characteristics. These characteristics are the litmus test that separates legacy-hosted infrastructure from true cloud computing, and they are critical for determining the scope of your audit. If these traits are absent, you are likely auditing a static data center environment rather than a cloud-native architecture. As an auditor, your first step is always to verify that the target environment actually adheres to these essential tenets. Without this baseline, your control assessments will lack both context and technical accuracy. The first characteristic, on-demand self-service, signifies that a consumer can unilaterally provision computing capabilities without requiring human interaction with the service provider. From an auditing perspective, this implies that you must examine the documentation surrounding automated provisioning portals and programmatic interfaces. We need to verify that access controls governing these environments are robust, as they represent the primary entry point for managing resources. If manual intervention is required for minor shifts in capacity, the service fails this criterion. The second characteristic is broad network access, meaning capabilities are available over the network and accessed through standard mechanisms that promote use by heterogeneous, thin or thick client platforms. This entails auditing the underlying network architecture to ensure security boundaries are enforced consistently across diverse access points. You must ensure that the transition from a private office network to a public internet connection does not bypass established security policies. Resource pooling constitutes the third essential characteristic, representing the provider's ability to serve multiple consumers using a multi-tenant model. Physical and virtual resources are dynamically assigned and reassigned according to consumer demand, creating a significant audit challenge regarding data isolation. You must investigate how the provider logically segments memory, processing power, and storage to prevent cross-tenant data leakage. This is where we look for evidence of robust logical isolation and hypervisor security, ensuring that one tenant's actions cannot influence or access another tenant's private environment. The fourth characteristic, rapid elasticity, allows for seamless scaling of resources up or down, often automatically, to match demand. Auditors frequently overlook the security implications of this scaling, specifically how security policies are pushed to new, ephemeral instances simultaneously. We must verify that the security configuration remains consistent as the infrastructure footprint fluctuates, preventing a situation where a new instance is launched without the required security controls. Measured service, the final characteristic, ensures that cloud systems automatically control and optimize resource use by leveraging a metering capability. This is essential for transparency and billing, providing insight into the consumption of processing, storage, and active user accounts. For the auditor, this serves as a critical data point for verification, as logs generated by the metering system provide an objective audit trail of resource utilization. You should evaluate how these metrics are protected from unauthorized alteration, as they directly impact both financial billing and operational security awareness. If a provider cannot demonstrate accurate, tamper-evident measurement, the reliability of the entire cloud service model comes into question. By validating these 5 characteristics, you establish that the environment possesses the structural properties inherent to cloud computing, which then dictates the depth and focus of your subsequent audit procedures. I will see you in the next lecture. Welcome back. Today, we move our focus to the foundational layer of the cloud stack, which is infrastructure as a service. Infrastructure as a service, or IaaS, represents the fundamental building block where a cloud provider offers virtualized computing resources over the internet. When we audit IaaS environments, we are essentially looking at how the vendor manages the hypervisor and how they provide the underlying compute, storage, and networking hardware to the tenant. Unlike legacy on-premises environments, IaaS abstracts the physical hardware layer. Yet, as auditors, we must verify that the abstraction does not lead to a loss of control or visibility. Providers may offer both multi-tenant virtualized environments and dedicated bare metal provisioning for users who require physical isolation or performance predictability. Your objective as an auditor is to map these technical implementations against the Cloud Security Alliance Cloud Controls Matrix to ensure that isolation boundaries remain intact and effective. You should investigate how the provider manages hypervisor updates, as vulnerabilities at this layer potentially expose all hosted virtual machines to cross-tenant attacks or unauthorized lateral movement. Auditing the IaaS requires a rigorous evaluation of the shared responsibility model, specifically identifying where the provider's authority ends and the tenant's domain begins. At a minimum, the provider is responsible for the physical data center security, the hypervisor, and the managed networking fabric. However, the tenant remains fully responsible for the security of the operating systems they deploy, the applications they install, and the data stored within their virtual disks. During an assessment, you must verify that the tenant has implemented protective controls, such as host-based firewalls, identity and access management for operating system users, and encryption at rest for storage volumes. If you observe a lack of clear documentation regarding these delineations in the service agreement, you must report this as a risk, as it often leads to catastrophic security gaps during incident response. Evaluating a service provider's white papers and independent attestation reports, such as those compliant with SOC 2 or ISO 27017, is essential to validate that their control objectives align with your organization's security posture. Operational control validation in the IaaS space necessitates deep integration with monitoring and logging mechanisms provided by the vendor. You should ask to see evidence of continuous auditing of the configuration state of virtual machine instances, especially in hybrid or multi-cloud environments. Risk mitigation here often involves verifying that the organization uses automated tools to detect drift from their approved machine image baseline. Furthermore, you must ensure that incident response plans account for the volatile nature of cloud environments. where instances might be terminated or repurposed before forensic evidence can be gathered. It is your responsibility to confirm that providers allow for the integrity of logs and that these logs are exported to a secure, immutable storage location outside the direct reach of the production compute nodes. Without this separation, an attacker with root access to an instance could potentially clear their tracks and evade detection. Data protection and regulatory compliance form the final pillar of an effective IaaS audit strategy. You need to verify if the provider supports encryption of data at rest and in transit, and how they manage the underlying cryptographic keys. When dealing with regulated environments, data sovereignty becomes a critical concern, as you must confirm that the physical region where the storage resides complies with jurisdictional requirements. If an organization opts to bring their own keys, you must audit the key management lifecycle, starting from generation and ending with secure decommissioning. Additionally, verifying SLA monitoring ensures that the provider is meeting its uptime and security availability commitments, which are crucial for maintaining the resilience of your architecture. Remember that even with the best provider controls, any technical configuration that ignores the principle of least privilege or leaves management ports exposed to the public internet will inevitably fail an audit. I look forward to discussing how these concepts translate into your practical audit work in our next session. Welcome back to our exploration of cloud service models. Today, we will focus on Platform as a Service, or PaaS, and how it fundamentally shifts the audit landscape compared to lower-level infrastructure services. Platform as a Service provides a framework that allows developers to build, deploy, and manage applications without the underlying complexity of maintaining servers, operating systems, or storage hardware. When we evaluate PaaS from an auditing perspective, we are shifting our attention away from the patch management of the virtual machine and toward the security of the developer runtime environment and middleware. The provider assumes responsibility for the abstracted layers, but as auditors, we must verify that the provider's operational controls for those layers meet our organizational risk appetite. We need to examine how the PaaS environment integrates with existing database services and whether the orchestration frameworks are configured to isolate tenant workloads effectively. Because the tenant has less visibility into the host operating system, we must rely more heavily on vendor-independent attestation reports such as SOC 2 or CSA star certifications. This transition requires a change in mindset, as we are no longer auditing the server hardening process itself, but rather the configuration security of the platform services the vendor provides. Auditing PaaS requires a rigorous assessment of the shared responsibility model, specifically looking at where the provider's obligations end and the tenant's management begins. A primary concern is the orchestration framework, which controls how applications are deployed and scaled within the environment. If your organization uses containerized workloads or serverless functions, the configuration of the service mesh and the API gateway becomes the primary audit boundary. You should review how identity and access management policies are enforced at the project or namespace level, ensuring the principle of least privilege is maintained by developers. Furthermore, we must evaluate the data protection strategies provided within the platform, such as transparent data encryption and managed cryptographic key services. Are the platform-level logs sufficiently granular to reconstruct events in the event of an incident? We must ensure that audit trails are not just available, but are also exported to an immutable, external monitoring system that remains independent of the cloud provider's own administrative access. When assessing technical and administrative controls in a PaaS context, we cannot overlook the importance of continuous monitoring and vulnerability management. Even though the provider handles the middleware patching, we remain responsible for the security of the application code we deploy and the specific configurations we apply to the platform. Auditors must verify that there is an automated mechanism to scan the infrastructure as code templates or deployment scripts for common security misconfigurations before they reach production. One must also evaluate the resilience of the architecture by reviewing the multi-region capabilities and the configuration of service-level agreements to ensure they account for platform availability. Data sovereignty is another critical dimension, especially if the PaaS utilizes distributed database services that might replicate data across jurisdictional boundaries. An effective audit must validate that the provider's compliance mapping aligns with the specific regulatory requirements governing your industry, such as GDPR or HIPAA, specifically regarding data at rest and in transit. Effective evaluation of these distributed systems relies on gathering objective evidence that confirms the effectiveness of the controls in place. We should look for evidence of penetration testing results, specifically focusing on the interface between the cloud-native application and the underlying platform services. The audit should also document how the organization performs remediation tracking for vulnerabilities identified by the cloud provider or through internal assessment tools. If the platform supports third-party integrations, we have to consider the supply chain risks associated with those middleware components and ensure they are adequately vetted. This approach ensures that we are applying traditional audit rigor to dynamic, virtualized environments without losing sight of the underlying security objectives. By prioritizing these architectural validations, we can provide assurance that the PaaS implementation contributes to, rather than undermines, the security posture of the enterprise. I will see you in the next lecture. Welcome back. Today we examine software as a service, commonly known as SaaS, focusing on its architecture and the specific audit requirements it imposes on your organization. Software as a service represents the top layer of the cloud computing stack, where a provider manages the entire infrastructure, platform, and application runtime, leaving the customer responsible primarily for data and user access. The core architecture underpinning most SaaS solutions is multi-tenancy, which allows a single instance of software to serve multiple organizational customers simultaneously. From an auditor's perspective, the primary concern here is data isolation, ensuring that one tenant cannot access, view, or influence the data belonging to another. We look for logical separation mechanisms, such as tenant-specific database schemas or row-level security policies enforced at the application layer. When APIs are involved to facilitate interoperability between the SaaS platform and your internal systems, the audit focus shifts to authentication, authorization, and the integrity of the data in transit. You must verify that the provider's API documentation aligns with the actual technical implementation and that rate limiting is in place to prevent resource exhaustion or unauthorized data scraping. When evaluating the stability and security of a SaaS solution, we rely heavily on the Cloud Security Alliance Cloud Controls Matrix, or CCM, and the Consensus Assessments Initiative Questionnaire, or CAI. These frameworks provide the granular control objectives necessary to assess both technical and operational posture in a shared responsibility environment. You need to verify the provider's commitment to service-level agreements, specifically examining the metrics used to track availability, latency, and throughput. It is not enough to simply review the contract. You must ensure the provider demonstrates continuous auditing through SOC 2 Type 2 reports or CSA star attestation. During an audit, pay close attention to the incident response procedures and how the provider communicates breach notifications to tenants. In a mature SaaS environment, there should be clear evidence of vulnerability management, effective change control processes, and regular third-party penetration testing that covers both the application logic and the underlying infrastructure. Data protection is arguably the most critical pillar when auditing SaaS, requiring a deep dive into encryption standards and key management lifecycles. Even though the provider manages the application, you must ascertain whether they support bring your own key strategies, which allow the tenant to retain control over the root of trust. If the provider manages the keys on your behalf, you need to audit their logical access controls to ensure that no unauthorized administrative account can expose your encrypted data. Data sovereignty is another hurdle, especially when dealing with SaaS vendors that distribute data across multiple geographic regions to achieve high availability. You must request documentation confirming that data storage locations align with your regulatory obligations, such as GDPR or local jurisdictional requirements. Effective auditing in this space requires moving beyond static point-in-time assessments toward a model that leverages automated logs and real-time monitoring alerts provided by the vendor. Finally, we must consider the risk associated with supply chain dependencies and the configuration of the SaaS environment itself. SaaS applications are often integrated into a larger ecosystem, creating an expanded attack surface that requires rigorous identity and access management controls. When auditing these configurations, verify that the principle of least privilege is applied to all service accounts, and that multi-factor authentication is enforced across the tenant portal. Organizations frequently overlook the necessity of auditing the SaaS provider's own third-party risks, yet this is vital for ensuring long-term resilience in a hybrid cloud topology. If you find that the provider lacks transparency regarding their sub-processors or if their attestation reports contain significant qualified opinions, you must flag this as a critical deficiency. Remediation tracking should be a collaborative effort between the provider's technical contact and your security team to ensure that audit findings are not just documented, but addressed in a timely manner. I look forward to our next session. Welcome back. Today we examine cloud deployment models and their implications for the auditing process. When we talk about cloud deployment models, we are effectively talking about the boundaries of trust and control. NIST identifies public, private, community, and hybrid models. But from an auditing perspective, these definitions represent varying degrees of architectural isolation and responsibility. A public cloud environment means infrastructure is provisioned for open use by the general public, often resulting in multi-tenant architectures where your data resides alongside that of other organizations. Your primary concern here is the logical isolation provided by the hypervisor or container runtime, as physical control is entirely surrendered to the service provider. An auditor must therefore shift focus from physical security checks to evaluating the effectiveness of the provider's logical access controls and multi-tenancy isolation mechanisms. Without this shift, you are simply auditing a black box that you have no authority to inspect directly. Private clouds present a different set of challenges, as they are operated solely for a single organization, whether managed internally or by a third party. While this retains the elasticity of the cloud, it often leads to a false sense of security, where the organization assumes that private ownership inherently equates to better compliance. In reality, a private cloud often shifts the burden of maintaining security patches, hardware integrity, and infrastructure configuration back to the internal IT team. As auditors, we must scrutinize the management plane of these private clouds with the same rigor we would apply to any on-premises data center. The distinction lies in whether the infrastructure is dedicated, which simplifies the scope of vulnerability assessments, but complicates the assessment of physical facility security. We must ensure that the administrative controls governing these environments are as robust as those in a public cloud, if not more so. Community cloud models add a layer of complexity by sharing infrastructure between organizations with shared concerns, such as specific regulatory requirements or industry-standard security baselines. This model is common in sectors like healthcare or government agencies where data sovereignty and specific jurisdictional requirements dictate a collaborative approach to resource management. When auditing this, your mandate includes evaluating how the community manages identity and access to prevent lateral movement between participating entities. You are no longer just looking at a single client-provider relationship. You are auditing a decentralized ecosystem where the configuration choices of one member could potentially impact the security posture of another. This requires a granular review of the governance agreements and the shared responsibility matrices that underpin the community's operations. Hybrid cloud deployment bridges the public and private worlds, and it is here that the majority of modern enterprise architectures reside. The audit of a hybrid model is essentially an audit of the connectivity, data flow, and identity federation between disparate environments. You need to investigate the security of the APIs and middleware that bridge the gap, as the perimeter is no longer a static physical line, but a complex web of services. Data protection, including encryption in transit and at rest, becomes the primary point of failure if the hybrid configuration lacks adequate synchronization. Auditors must verify that policies applied to the private environment are consistently enforced in the public cloud, ensuring that the security posture does not degrade as workloads migrate. Understanding these models allows us to align our audit methodology with the specific risk profile of the infrastructure being evaluated. See you in the next lecture. Welcome to this analysis of the shared responsibility model, a critical concept for any cloud auditor. In this session, we will dissect the functional boundaries of security and compliance between providers and tenants. The shared responsibility model functions as a foundational contract that determines who is responsible for specific security controls within a cloud environment. It is not merely a theoretical framework, but a practical tool for delineating where the cloud service provider's accountability ends and where the tenant organization's obligations begin. As auditors, we must understand that this division of responsibility shifts based on the service model, whether it is IaaS, PaaS, or SaaS. In an IaaS deployment, the provider secures the physical infrastructure and the virtualization layer, while the tenant assumes responsibility for guest operating systems, application configurations, and data. Conversely, in a SaaS model, most of the infrastructure and application security stack is managed by the provider, leaving the tenant primarily responsible for identity management and data configuration. Misunderstanding these boundaries is a leading cause of misconfigured cloud resources and subsequent data breaches. You should approach every audit engagement by first verifying if the organization has clearly documented its interpretation of this model in its internal policy and external vendor contracts. When we examine the control objectives defined in frameworks like the CSA Cloud Controls Matrix, it becomes evident that the shared responsibility model is dynamic rather than static. Audit evaluation methodologies must account for the fact that even if a provider is responsible for a specific control, such as physical security, the tenant must still verify the effectiveness of those controls through independent third-party attestations. We cannot simply take a provider's marketing collateral at face value when conducting an audit that requires evidence of compliance. Instead, we look for SOC 2 Type 2 reports, or ISO IEC 27001 certifications, as evidence that the provider's controls meet the stated requirements. The burden of proof remains on the tenant to ensure that the provider's security controls adequately cover the risks associated with the tenant's specific data assets. This process requires a systematic mapping of technical, operational, and administrative controls to ensure no gaps exist in the combined security posture. Auditors must also contend with the complexities introduced by hybrid and multi-cloud architectures, where responsibility matrices can become incredibly convoluted. In these environments, the organization might simultaneously manage on-premises hardware, a virtual private cloud, and several software-as-a-service providers. Each of these components requires its own unique mapping of security obligations and risk ownership. You should specifically focus on how the organization monitors its service-level agreements to ensure that the provider is meeting its uptime and security commitments. If a vulnerability is discovered in the underlying virtualization layer, the responsibility for patching lies solely with the provider. Yet the tenant's incident response plan must account for how they will manage their internal response during a provider-side outage. This necessitates strong collaboration between the business, IT, and internal audit functions to maintain a cohesive approach to risk management. When evaluating the effectiveness of these distributed responsibilities, we must rely on data-driven metrics rather than qualitative assumptions. The implementation of identity and access management serves as an excellent litmus test for verifying that the shared responsibility model is being applied correctly. In most cloud environments, the provider offers the platform and the tools for access control, while the tenant is strictly responsible for managing user accounts, roles, and permissions. If an auditor finds that a tenant has not implemented multi-factor authentication for their cloud console, that is a failure in the tenant's execution of their shared role, not a failure of the provider. Furthermore, data protection strategies, including encryption and key management, are almost always the tenant's primary domain, regardless of the service model. We must inspect how keys are stored, rotated, and protected to ensure that the tenant has not inadvertently left their data exposed, despite the provider giving them the necessary tools to secure it. Finally, we must consider the legal and regulatory implications of responsibility mapping, particularly regarding data sovereignty and jurisdictional requirements. Even if a provider manages the data centers, the tenant is often legally liable for the residency and privacy of the regulated data stored within those regions. An audit is incomplete if it fails to verify whether the organization has addressed these legal requirements through their provider contracts. We look for specific clauses that define the provider's duty to inform the tenant of any law enforcement requests or sub-processor changes that might impact the data's integrity. When auditing supply chain risks, we ensure that the organization maintains oversight of their provider's third-party relationships as well. The ultimate goal is to generate an audit report that clearly documents where risks are accepted, where they are mitigated by the provider, and where internal controls are currently insufficient to meet the organizational risk appetite. I will see you in the next lecture. Welcome to this segment on IT governance alignment. In this chapter, we will focus on bridging the gap between high-level business strategy and the technical realities of cloud adoption. Cloud governance is not a solitary technical exercise, but a foundational requirement for organizational success. Proper alignment ensures that your enterprise IT governance frameworks do not conflict with the strategic objectives of cloud migration. When we discuss board-level visibility, we are essentially talking about translating abstract risks into business impact parameters that executives can understand and act upon. Without executive sponsorship, cloud deployments often succumb to shadow IT practices, which bypass established security controls and create blind spots for the audit function. An auditor must evaluate whether the organization has successfully extended its governance mantle over the cloud environment, rather than treating the cloud as a separate, isolated silo. This requires mapping existing corporate policies to the dynamic nature of virtualized infrastructure, ensuring that administrative controls remain as rigorous as they are on premises. When evaluating the effectiveness of governance alignment, one must look at how the organization defines and assigns responsibilities within the shared responsibility model. You are not auditing the cloud service provider itself, but rather the effectiveness of the tenant in fulfilling their specific obligations as outlined in the service contract. This process involves a deep look into the Cloud Security Alliance Cloud Controls Matrix and the Consensus Assessments Initiative questionnaire to identify if the control objectives are met. Technical controls, such as those related to identity and access management or encryption, must be audited not just for their presence, but for their alignment with the overarching risk appetite defined by the board. If the governance framework does not mandate multi-factor authentication or data sovereignty controls, these measures may fail during a compliance validation, despite being technically implemented. Therefore, consistency between corporate policy and technical implementation remains our primary audit focus. The complexity of modern cloud deployments, particularly in hybrid or multi-cloud environments, necessitates a shift in how we approach audit rigor. We must verify that the organization has processes in place to continuously monitor service-level agreements, as the cloud provider's performance is directly coupled with the tenant's ability to maintain compliance. Incident response, forensics, and vulnerability management cannot be reactive functions managed solely by a technical team. They must be integrated into the governance structure through documented, tested, and approved procedures. Furthermore, when dealing with microservices and containerized workloads, governance must evolve to cover the orchestration plane and the secure configuration of the supply chain. If the governance framework does not account for the rapid lifecycle of these workloads, it will inevitably become obsolete, leading to potential security gaps that an auditor would identify as a failure in oversight. Auditors must also ensure that there is a clear mechanism for reporting deficiencies and tracking remediation efforts. A finding is only as valuable as the evidence that shows it has been corrected within an acceptable timeframe. This phase of the audit cycle requires the organization to demonstrate how they evaluate the effectiveness of their chosen controls, often utilizing automated assessment tools that provide a near real-time view of the configuration state. By mapping traditional control objectives to cloud-native implementations, we ensure that the business strategy remains secure and resilient. Ultimately, independent attestation reports and vendor-provided security documentation should be treated as pieces of evidence in your broader evaluation, rather than wholesale validation of the environment. Our objective is to confirm that the organization maintains control, accountability, and transparency across the entire distributed system. See you in the next session. Welcome back. In this lesson, we will focus on the fundamental pillars of formulating a cloud strategy that aligns with both business objectives and rigorous audit expectations. Cloud strategy formulation is not merely about choosing a provider or migrating existing servers. It involves a deliberate alignment between your organizational readiness and the architectural principles required for a secure, scalable cloud footprint. When you start formulating this strategy, you must first assess whether your current operational processes can handle the transition to a dynamic, virtualized environment. This requires a shift in how you view infrastructure, moving away from static on-premises mindsets toward agile, software-defined architectures. Establishing a secure baseline for your multi-cloud environment is essential, as the lack of a unified configuration standard often leads to significant control gaps. You need to define these architectural principles early in the process to ensure that security is baked into the foundation rather than treated as an afterthought during the migration. A robust strategy acknowledges the complexity of hybrid configurations and explicitly maps out how security policies will be enforced across heterogeneous platforms. Without a clear strategy, your governance team will be unable to demonstrate consistent oversight, which is a critical failure point during an audit. As auditors, we must evaluate the efficacy of a cloud strategy by looking at how well it integrates with the shared responsibility model. You cannot simply outsource business risk to a cloud service provider, even if the primary security controls are managed by them. Your strategy must clearly delineate between the obligations of the provider and those of the tenant, with specific documentation covering jurisdictional requirements and data sovereignty. When reviewing a strategy, I look for evidence that the organization has mapped its internal control objectives against industry-recognized frameworks, such as the Cloud Security Alliance Cloud Controls Matrix. If this mapping is absent, the organization cannot verify if its control environment is actually covering the unique risks posed by cloud delivery models. Furthermore, your strategy must address the reality of third-party supply chain risks, which have become a primary vector for modern attacks. An effective plan includes mechanisms for continuous compliance validation and the periodic review of vendor-independent attestation reports. The technical, operational, and administrative controls you select must be audit-ready from day one. In a mature cloud strategy, there is a clear distinction between how you manage identity and access compared to traditional directory services. You should see evidence of centralized identity management policies that extend across all cloud accounts and integrated SaaS applications. When we talk about data protection, your strategy needs to define specific encryption standards and formal key management lifecycle processes. If the organization fails to explain how cryptographic keys are rotated and secured, an auditor will immediately flag the implementation as high risk. Additionally, the strategy must account for the ephemeral nature of microservices and container workloads, which require automated security validation rather than manual spot checks. This requires an integration of security into the development pipeline, often referred to as DevSecOps, to ensure that architectural changes do not invalidate existing security baselines. Finally, successful cloud strategy formulation involves planning for resilience and incident response within a multi-cloud context. You must evaluate how the organization monitors service-level agreements, as these often contain the only contractual bridge to operational visibility. During an audit, I look for evidence that the organization has tested its recovery plans and understands the limitations of the provider-supplied security tools. If the strategy does not define how logs are aggregated and analyzed for security events, the organization is effectively blind to ongoing unauthorized activities. An objective, independent assessment should confirm that the strategy is not just a theoretical document, but a working plan that facilitates ongoing monitoring and remediation. When business and IT strategies are properly aligned, the transition to the cloud becomes an opportunity to strengthen your security posture rather than a source of persistent audit findings. By focusing on these structured, measurable components, you provide clear guidance that sustains both compliance and operational integrity over time. See you in the next lecture. Welcome back to our discussion on navigating the complexities of cloud governance. Today, we focus on cloud risk management, a critical function that bridges the gap between traditional enterprise oversight and the fluid nature of shared cloud environments. Risk management in the cloud necessitates a shift from static asset protection to a dynamic, continuous evaluation process. When we talk about cloud risks, we are essentially looking at how traditional threat vectors intersect with infrastructure managed by a third party. The primary challenge is that you no longer have direct visibility into the hardware or physical isolation layers, meaning your risk assessment framework must rely heavily on the shared responsibility model. To manage this, ISACA and CSA frameworks emphasize the necessity of integrating cloud-native security controls directly into your organizational risk register. This requires a granular understanding of which controls are tenant-managed versus provider-managed. Effective risk assessment here involves mapping specific vulnerabilities, such as misconfigured storage buckets or overly permissive identity and access management policies, against established control objectives like those found in the Cloud Controls Matrix. By adopting a structured methodology, you ensure that risk identification remains objective rather than based on assumptions about provider security. Once risks are identified, the next phase involves treating these vulnerabilities through a combination of technical, operational, and administrative controls. Think of this as the enforcement layer of your risk strategy, where you must validate that the controls are not only deployed, but are also effective in the context of a distributed system. For instance, when dealing with data encryption or key management, you must evaluate how the provider handles cryptographic secrets and whether your organization retains sufficient control to meet compliance requirements. It is a common mistake to assume that a SOC report automatically covers your specific business risks, but the reality is more nuanced. You are responsible for auditing whether the provider's attested security posture aligns with your specific data sovereignty and jurisdictional requirements. Consequently, your assessment criteria must cover the full life cycle of the service, including how the provider manages incident response, forensic investigations, and the decommissioning of resources. Continuous auditing stands as the bedrock of modern cloud risk management because traditional point-in-time snapshots are insufficient for environments that change via infrastructure as code. Vulnerability management in this context isn't just about scanning. It involves real-time monitoring of configurations and automated policy enforcement. You should look for evidence that the provider supports your need for transparency, especially regarding how they manage supply chain risks when utilizing third-party libraries or managed services. By evaluating service-level agreements, you can determine if the provider's availability and security guarantees actually mitigate the risks identified in your impact analysis. Reporting deficiencies is not merely an administrative exercise. It must be part of a remediation tracking process that feeds back into your overall business IT strategy. When you maintain this rigor, you demonstrate that your audit activities provide actual value by verifying that security architecture remains resilient against both external threats and internal operational failures. See you in the next lecture. Welcome back. Let's dig into the strategic application of risk assessment frameworks within the context of cloud computing. We will focus on how classical methodologies translate into the dynamic reality of modern virtualized environments. When we shift from on-premises data centers to the cloud, the underlying risk assessment methodology must adapt to accommodate the shared responsibility model. Traditional frameworks like NIST SP 830 or the Octave Allegro approach remain conceptually relevant, but their execution requires significant tuning to address cloud-specific control ownership. In a cloud environment, you are not merely assessing your own hardware, you are validating the efficacy of controls managed by a third party. This shift necessitates a thorough review of the Cloud Security Alliance Cloud Controls Matrix and the Consensus Assessments Initiative questionnaire. These tools allow auditors to map high-level regulatory requirements directly onto the operational reality of cloud service provider landscapes. Without this mapping, auditors often fail to distinguish between risks the tenant can control and those that reside entirely within the provider's operational remit. Effective auditing in the cloud relies on balancing technical, operational, and administrative controls. Technical controls include elements such as cryptographic key management, identity and access management, and automated monitoring. However, the audit cannot stop at the technical layer. It must evaluate administrative governance through policies, contractual agreements, and vendor-provided attestation reports like SOC 2 or ISO 27017. When you assess a cloud environment, you must differentiate between the configuration of the workload, which is usually your responsibility, and the underlying infrastructure security, which is the provider's burden. An auditor must verify that the tenant has implemented robust technical controls to compensate for the reduced visibility into the provider's physical or hypervisor layers. This holistic view ensures that your risk management strategy addresses the entirety of the attack surface, including the complexities of microservices and containerized workloads. Continuous auditing and monitoring have replaced the static annual audit cycles of the past. In a cloud-native architecture, infrastructure changes constantly through automated deployment pipelines. Consequently, auditors must verify that continuous assurance frameworks are active to identify configuration drift or security vulnerabilities in real time. This requires an understanding of how vulnerability management tools and cloud-native logging mechanisms feed into the overall risk posture. If an organization fails to monitor its cloud environment continuously, it creates blind spots where misconfigurations can persist for months, leaving data exposed. Your role as an auditor is to ensure that the automation responsible for deploying infrastructure is also responsible for maintaining security compliance in alignment with established SLOs and SLAs. Addressing third-party and supply chain risks remains a critical component of modern risk assessments. As organizations adopt hybrid and multi-cloud strategies, they often rely on a web of interconnected services, increasing the complexity of the digital supply chain. You must evaluate how the organization manages these external dependencies. This involves reviewing vendor-independent attestation reports, understanding jurisdictional data sovereignty requirements, and ensuring that encryption strategies provide meaningful protection from cloud provider access. When you evaluate the effectiveness of these controls, you are validating that the organization has the necessary oversight to mitigate risks stemming from their partners or cloud providers. Rigorous evidence gathering remains the foundation of this process, even when the underlying environment is ethereal and ephemeral. See you in the next lecture. Welcome back. In this lecture, we are going to explore the core principles of designing and implementing risk mitigation strategies specifically tailored for cloud environments. When we talk about risk mitigation in the cloud, we are essentially moving from a static, perimeter-based mindset to one that emphasizes dynamic, control-based assurance. The primary objective is to select strategies that address the residual risk remaining after inherent risks are identified and assessed. We categorize these controls traditionally as preventative, detective, or corrective, yet in a cloud setting, their delivery mechanism often shifts toward automation and programmatic enforcement. For instance, a preventive control might manifest as an infrastructure as code template that prevents non-compliant storage buckets from being provisioned in the first place. A detective control is rarely a manual log review these days. Instead, it involves automated cloud-native monitoring tools that trigger alerts when they observe anomalous API calls or unauthorized attempts to access management planes. Meanwhile, corrective controls must be capable of auto-remediation, such as a function that automatically shuts down or isolates a compromised compute instance without requiring human intervention. To evaluate these strategies effectively, we must strictly adhere to the shared responsibility model, which serves as our primary frame of reference for auditing. The burden of mitigation is split between the provider and the tenant, and the lines of demarcation are never as clear as we might like them to be. When auditing, our goal is to verify that the tenant has effectively mapped their specific control objectives to the capabilities provided by the platform. This often involves reviewing the Cloud Controls Matrix or the Consensus Assessments Initiative Questionnaire to ensure that the providers attested security controls adequately, mitigate the threats identified in the tenant's risk profile. We are looking for tangible evidence that the tenant understands what they are responsible for, such as identity and access management configurations, data encryption at rest, and key management strategies, while acknowledging that the provider manages the underlying hardware, firmware, and virtualization layers. Operational and administrative controls are just as critical as technical ones in this domain. A common pitfall for organizations migrating to the cloud is focusing solely on the technical implementation of encryption while neglecting the administrative rigor required to manage cryptographic keys. An auditor must assess whether there is a lifecycle policy in place, how keys are rotated, and who holds the access rights to the key management system. Furthermore, regulatory compliance and data sovereignty must be woven into the strategy, particularly when dealing with hybrid or multi-cloud architectures. If an organization operates in a jurisdiction with strict residency requirements, their mitigation strategy must include technical constraints that ensure data cannot traverse prohibited geographic regions. This requires a sophisticated verification process involving the review of independent attestation reports like SOC 2 or STAR certifications to confirm that the provider's controls remain effective over time. Ultimately, the effectiveness of your risk mitigation strategy hinges on your ability to validate the security state continuously. Traditional point-in-time auditing is insufficient for systems that change as rapidly as microservices running in containers. Your assessment methodology must pivot toward continuous auditing principles, where compliance is treated as a state that is measured continuously rather than a periodic event. This necessitates an understanding of how to audit the DevSecOps pipeline, ensuring that security validation is integrated into the build process itself. If the pipeline can prove through automated testing that every containerized workload adheres to defined hardening standards, then the audit burden shifts from manual inspection of each instance to an audit of the pipeline's integrity. This shift in focus is what distinguishes a mature cloud security professional from someone still applying legacy on-premises mental models to modern cloud platforms. See you in the next lecture. Welcome back, and let's examine the role of metrics in maintaining effective cloud governance. In any complex system, What you cannot measure, you cannot effectively control or govern. When we talk about cloud governance metrics, we are essentially building a bridge between high-level business objectives and the day-to-day reality of our virtualized infrastructure. These metrics serve as the heartbeat of your security posture, providing the empirical data required to validate that your administrative, technical, and operational controls are not just designed correctly, but are performing as intended. You need to distinguish between key performance indicators, which measure the efficiency and effectiveness of your cloud operations, and key risk indicators, which act as early warning signs for potential security drift or compliance failures. For instance, a KPI might track the percentage of automated deployments that successfully pass the security baseline check, while a KRI could monitor the rising frequency of unauthorized access attempts against specific cloud storage buckets. Establishing these metrics requires a deep understanding of the shared responsibility model, as you must only track and report on controls that fall under your purview as a tenant. Without this clarity, you risk cluttering your dashboard with noise that belongs to the cloud provider, ultimately obscuring the actual risks your organization faces in the production environment. The shift from traditional periodic auditing to continuous monitoring necessitates a move toward automated collection of evidence. You cannot rely on static spreadsheets or annual manual reviews when dealing with elastic microservices-based workloads that change every hour. Instead, you need to embed data collection into your CI/CD pipelines and infrastructure as code templates, ensuring that every deployment is cryptographically signed and its configuration state is recorded. This allows you to evaluate your control effectiveness against the CSA Cloud Controls Matrix in real time rather than retrospectively. When you review vendor-provided attestation reports such as a SOC 2 Type 2 or a STAR certification, your metrics should reflect how well the provider's reported controls align with your internal risk appetite. You are looking for anomalies, unexpected spikes in identity access management changes, or deviations in key management usage that indicate a potential breach or misconfiguration. These metrics provide the raw material for your deficiency reporting and remediation tracking, ensuring that when an issue arises, you have the historical data to analyze the root cause and execute a technical fix. Auditing within a hybrid or multi-cloud architecture adds another layer of complexity that your metrics must account for, particularly regarding data sovereignty and jurisdictional compliance. You need to track exactly where your data resides and which specific security controls are applied to that geographic location, as compliance validation is never one-size-fits-all across international boundaries. Furthermore, your metrics should encompass supply chain risks, verifying that third-party service providers are meeting their established service level agreements. If your SLA dictates a certain uptime or a mandated response time for incident resolution, your governance dashboard should automatically alert you when those thresholds are breached. This is where the distinction between qualitative assessment, which might involve interviewing process owners or reviewing policy documents, and quantitative assessment, which relies on log analysis and telemetry, becomes vital. By blending these two approaches, you create a robust assurance framework that proves not only that you have a policy in place, but that the policy is being enforced across every node of your distributed network. Ultimately, the goal of these governance metrics is to provide board-level visibility into IT strategy alignment while maintaining the rigor required for technical auditing. You should avoid the trap of measuring things simply because they are easy to measure, as vanity metrics provide a false sense of security while leaving real vulnerabilities hidden. Focus instead on actionable insights, data that directly informs whether you need to increase your investment in encryption, improve your container hardening, or revise your incident response procedures. When you present this data, it should map clearly back to your business goals, demonstrating that security is an enabler of growth rather than a bottleneck. As you refine these metrics over time, they will become the primary source of truth for your compliance validation, significantly reducing the stress and duration of your formal audit cycles. By maintaining objective independence through automated assessment tools, you transform the audit function from a reactive audit activity into a proactive component of your cloud architecture. I look forward to seeing you in the next lecture. Welcome back. In this session, we will explore the Cloud Security Alliance Security Trust Assurance and Risk Program, often referred to simply as the CSA STAR. The CSA STAR program serves as a critical pillar for verifying cloud provider security posture through a multi-tiered framework. It is designed to provide transparency by allowing organizations to assess their cloud service providers against standardized control objectives. The program rests on two primary foundations: the Cloud Controls Matrix and the Consensus Assessments Initiative Questionnaire. By leveraging these tools, auditors can move beyond mere marketing claims and start evaluating hard technical, operational, and administrative controls. Think of this as your primary mechanism for performing due diligence in a standardized, repeatable fashion. When you audit a provider, you are looking for evidence that their internal security practices align with industry-recognized frameworks rather than relying on private, non-verifiable documentation. This shift toward public transparency is what makes the STAR program so valuable for those tasked with third-party risk management in complex cloud ecosystems. The Cloud Controls Matrix, or CCM, is essentially a controls framework that maps security controls to trusted standards and industry best practices. It serves as an authoritative bridge, connecting the high-level governance requirements of an organization to the granular technical controls implemented by the provider. When you are auditing a cloud environment, the CCM provides the audit criteria you need to measure control effectiveness. It covers everything from application and interface security to physical and environmental security. For an auditor, this is not just a list of to-do items, but a comprehensive inventory of your shared responsibility delineations. Each control is carefully mapped to reveal whether the responsibility lies with the provider, the tenant, or is a shared effort. Understanding where that line is drawn is perhaps the most critical part of your job when evaluating a cloud architecture. If the CCM is the framework, then the Consensus Assessments Initiative Questionnaire, or CAIQ, is the standardized way to query that framework. It acts as a comprehensive set of questions that a tenant can use to assess the security capabilities of a cloud provider. Unlike a long-form request for proposal, the CAIQ is designed to be machine-readable and standardized across the industry. When you work with this questionnaire, look for the evidence behind the answers rather than just accepting a yes checkbox. Many providers provide a completed CAIQ as part of their transparency documentation, which allows you to perform an initial desk audit before you ever engage in more intensive testing. This saves time and resources, allowing you to focus your audit rigor on the most critical gaps or high-risk configurations. If a provider cannot substantiate their CAIQ responses with audit reports or internal assessments, then you have found yourself a red flag. The STAR program is further structured into tiers, moving from self-assessment to independent third-party audits and eventually to continuous monitoring. Level 1, the self-assessment, is where you start to see the initial level of provider transparency, though it requires a grain of salt because it lacks external validation. Level 2 involves an independent audit performed by a third party, which provides a significantly higher level of assurance regarding the effectiveness of implemented controls. Level 3, while less common, deals with continuous cloud monitoring to provide real-time assurance, which is the current gold standard. As an auditor, your role is to review these reports for independence and scope. You need to ensure that the attestation matches the environment you are actually consuming, rather than a generic statement about the vendor's infrastructure at large. When we analyze the effectiveness of these controls, we must focus on how they manage the life cycle of risks, including identity and access management and data protection. A provider might claim they are compliant with a specific standard, but evidence must verify that encryption is actually applied consistently across all data at rest and in transit. You should be looking for proof of key management strategies, such as how the provider handles rotation and revocation, instead of just the existence of an encryption policy. Furthermore, the STAR program encourages us to view compliance as a living process. It is about checking if the provider has the mechanisms in place to handle incident response and forensic analysis should a compromise occur. If a provider cannot explain how they track and remediate deficiencies, their adherence to a framework like the CCM is largely superficial. Finally, you must consider the geopolitical and regulatory implications of your cloud audit, especially concerning data sovereignty and jurisdictional requirements. The STAR program provides a structured way to evaluate where and how data is processed, which is essential for audit compliance. Map the control objectives provided in the CCM to your specific regulatory needs, such as GDPR or HIPAA, to ensure your business strategy stays aligned with your IT execution. Validating these controls in a hybrid or multi-cloud environment requires you to understand how the vendor's independent attestation reports cover your specific configuration. By maintaining objective independence throughout your assessment, you can ensure that the infrastructure you rely on is truly as secure as the documentation suggests. This discipline is what separates a meaningful audit from a simple paperwork exercise. See you in the next lecture. Welcome back. Today we examine the specific regulatory requirements and authorization procedures mandated by the Federal Risk and Authorization Management Program. FedRAMP provides a standardized approach to security assessment, authorization, and continuous monitoring for cloud products and services used by United States federal agencies. When we talk about this program, we are essentially discussing a framework built upon the NIST Special Publication 800-53, which is the foundational catalog of security and privacy controls. Achieving an authority to operate through this program requires a cloud service provider to demonstrate that they meet a specific baseline of controls, which are categorized into low, moderate, and high impact levels. These baselines act as a rigid checklist that ensures a consistent security posture across the federal cloud ecosystem, regardless of which specific vendor is providing the underlying infrastructure. From an auditor's perspective, this means you do not have to negotiate control requirements from scratch with every single provider. Instead, you rely on the predefined, rigorous set of requirements that the provider has already implemented and validated. The actual process of obtaining this authorization involves a specialized third party known as a 3PAO, or Third-Party Assessment Organization. These organizations are accredited by the FedRAMP Program Management Office to perform independent assessments of a cloud provider's security controls. As an auditor, you should understand that a 3PAO does not simply glance at a dashboard. They conduct an exhaustive evaluation of technical, operational, and administrative controls. They are looking for evidence, technical logs, configuration snapshots, and policy documentation that proves the control is not just present, but also operating as intended. This process culminates in a security assessment report, which acts as the official document capturing the assessment findings, which is then reviewed by the agency or the Joint Authorization Board. The rigor of this assessment is what makes FedRAMP a gold standard, even outside of purely federal contexts, because it forces a high level of transparency and documentation. Continuous monitoring is perhaps the most critical component if you are auditing within a FedRAMP environment. Once a cloud provider receives their authorization, the work is far from over because the underlying cloud infrastructure is dynamic and changes constantly. The provider must maintain an ongoing security posture by submitting regular vulnerability scan reports and managing a plan of action and milestones, commonly referred to as a POA&M. Your role as an auditor here involves verifying that the remediation tracking is not just a paper exercise, but a lived process where high-risk vulnerabilities are addressed within strict timelines. You would inspect how the provider monitors their environment for configuration drift, ensuring that the settings verified during the initial assessment have not been weakened by subsequent deployments or automated updates. This shifts the audit mindset from a point-in-time snapshot to a persistent state verification. When we map these activities to our broader frameworks like the Cloud Security Alliance Cloud Controls Matrix, we find that FedRAMP acts as a practical implementation layer for many abstract concepts. We look at data protection through the lens of encryption at rest and in transit, verifying that the Federal Information Processing Standards, or FIPS, are strictly followed for cryptographic modules. This is not just about using a standard library, but about ensuring the entire key management lifecycle, from generation to rotation and destruction, is auditable and robust. Furthermore, the shared responsibility model becomes acutely visible here, as the provider is responsible for the security of the infrastructure, while the tenant remains responsible for their own configuration, identity management, and data access policies. An effective audit evaluates this boundary to ensure that no critical security controls have fallen into the gap between the provider's managed services and the customer's implementation. Understanding the nuances of identity and access management is another pillar of this evaluation, particularly in how it pertains to administrative access to the underlying management plane. You must verify that the provider enforces multi-factor authentication for all users, and that the principle of least privilege is applied to service accounts and API access keys. If you are auditing a microservices or container-based workload, you need to extend this rigor to the orchestration layer, ensuring that the cluster configuration is hardened against unauthorized lateral movement. This also means reviewing the supply chain risks, as cloud providers often integrate third-party components or open-source libraries into their platforms. An auditor's competence is demonstrated by their ability to track these dependencies and verify the provider's independent attestation reports concerning their own software supply chain security. Effective auditing in this domain requires maintaining objective independence, regardless of the pressure to accelerate deployment cycles or cloud adoption goals. You should use automated assessment tools wherever possible to ingest configuration data and compare it against the FedRAMP control baselines, which reduces human error and improves audit repeatability. By focusing on evidence-based verification rather than vendor assertions, you maintain the integrity of the audit process. Remember that the goal is always to validate the security model's resilience against threats while ensuring that the business utility of the cloud environment is not unnecessarily impeded by these administrative hurdles. Evaluating these systems requires a disciplined approach, mapping technical findings directly back to the regulatory control objectives and identifying any deficiencies that could compromise the entire architecture. I will see you in the next lecture. Welcome back. In this session, we will examine the nuances of SOC reporting and how these documents function as cornerstones for evaluating trust services criteria in cloud environments. System and Organization Controls reports, commonly referred to as SOC reports, are independent assessments that provide auditors and customers with a window into the security posture of a service organization. When reviewing a SOC 1 report, we are primarily concerned with internal controls over financial reporting, which is a narrower scope than what most security professionals initially expect. In contrast, SOC2 reports focus on the trust services criteria of security, availability, processing integrity, confidentiality, and privacy. These reports are foundational because they map directly to the CSA Cloud Controls Matrix, allowing us to align a provider's operational realities with our specific risk requirements. A SOC3 report is essentially a summarized version of the SOC2, designed for general distribution, but it lacks the depth of evidence required for a rigorous internal audit. To truly evaluate these documents, you must look past the provider's assertion and focus intensely on the auditor's opinion and the description of the system. Remember that a clean opinion does not automatically imply that your data is secure, as it only confirms that the specified controls were functioning as described within the examination period. When deep diving into the technical, operational, and administrative controls within these reports, you must scrutinize the bridge between the provider's responsibilities and the tenant's obligations. The shared responsibility model is not merely a theoretical diagram, but a contractual reality that dictates who manages identity and access management, data encryption, and key management strategies. A common pitfall is assuming that because a report lists a control as effective, it covers your configuration of that service. You must verify if the provider offers the necessary tools for continuous monitoring and vulnerability management, or if those remain your responsibility as the tenant. For instance, while a cloud provider guarantees the security of the infrastructure, they rarely assume responsibility for misconfigurations in an Amazon S3 bucket or an improper Kubernetes security policy. Assessing these reports requires a granular mapping of control objectives to your internal compliance standards to ensure no gaps exist in your hybrid or multi-cloud architecture. Compliance validation depends on your ability to synthesize information from these reports to make objective decisions about third-party supply chain risks. You should be looking for evidence of how the provider handles incident response, forensics, and data sovereignty requirements, especially in distributed systems. If your organization operates across multiple jurisdictions, a global SOC2 report might not fully capture the regional nuances of localized data privacy laws. Furthermore, as organizations shift toward microservices and containerized workloads, the static nature of many SOC reports can become a limitation. You need to verify whether the provider's audit scope includes the underlying container orchestration layer, or if that is managed as an abstracted, unverified component. Always be wary of evidence that relies solely on management representation. Instead, search for testing procedures performed by independent auditors that provide actual validation of cryptographic implementation. Evaluating the effectiveness of these controls also means looking for deficiencies, which are often hidden in the nuanced language of the report's footnotes or the section detailing management's response. When a report identifies a deficiency, you must determine if the provider has a clear remediation tracking process and how frequently they undergo remediation validation. This requires a shift from viewing audit reports as simple check-the-box exercises to using them as analytical inputs for your broader security strategy. The goal is to move beyond the traditional trust but verify mentality and embrace one of validate and monitor. This involves integrating the findings from these reports into your continuous assurance framework, ensuring that the assurances provided by the vendor remain accurate between the yearly audit cycles. Aligning these insights with your business and IT strategies allows you to mitigate risks proactively rather than reacting to incidents after they occur. See you in the next lecture. Welcome back. Let us discuss how international standards ensure consistent security and privacy in cloud environments. We will focus specifically on how ISO 27017 and ISO 27018 act as essential extensions to your existing security framework. When we approach the audit of a cloud service provider, we rarely start from a blank slate because we rely on established international benchmarks to define our expectations. ISO 27017 serves as a vital extension to ISO 27002, specifically addressing the unique challenges posed by cloud computing by providing additional controls for both providers and customers. While ISO 27002 provides a broad baseline for information security, ISO 27017 refines these controls to address the shared responsibility model directly. For example, when auditing virtual machine security, you are not just checking if the host is patched, but how the provider manages the isolation between tenant instances. This standard forces a move away from generic security policies toward those that specifically recognize the ephemeral nature of cloud assets. If you are auditing an infrastructure as a service environment, you must verify that the provider implements the specific implementation guidance found in ISO 27017 to handle administrative access and incident reporting consistently. Without this alignment, your assessment risks becoming a subjective opinion rather than a rigorous audit based on globally accepted best practices. Privacy in the cloud requires an equally disciplined approach, which brings us to the importance of ISO 27018. This standard specifically addresses the protection of personally identifiable information in public clouds acting as processors of personal data. As an auditor, your task is to verify that the cloud service provider has implemented the robust controls required to ensure that personal data remains separated from other information and is processed only according to the customer's instructions. You need to look for evidence that the provider has clear policies regarding the disclosure of data to law enforcement and that they do not use customer data for their own marketing or advertising purposes without explicit documented consent. Encryption plays a central role here, as the standard requires that PII is protected during transit and at rest using methodologies that meet current cryptographic standards. When evaluating a provider's adherence to ISO 27018, you are fundamentally verifying the integrity of the data processing lifecycle, from initial collection to final disposal and return of data. To effectively audit these standards, you must map them against the CSA Cloud Controls Matrix and the Consensus Assessments Initiative Questionnaire to ensure comprehensive coverage. The goal is to evaluate technical, operational, and administrative controls within the context of the shared responsibility model. You are not simply checking a box to confirm that a control exists. You are assessing its implementation effectiveness through historical data, configuration reviews, and independent attestation reports. For instance, in a containerized workload, you must verify that the provider's segmentation controls align with the technical requirements established in the ISO framework. You are looking for artifacts that prove continuous monitoring, vulnerability management, and documented incident response procedures are active and responsive. This requires a shift in mindset because you are no longer auditing a static perimeter, but rather a dynamic, virtualized ecosystem where the controls must be as agile as the underlying infrastructure. Applying these international standards also demands a deep understanding of the provider's legal and jurisdictional obligations. Data sovereignty is not just a buzzword. It is a critical audit component where you must verify where the physical data resides and whether the provider's contractual obligations reflect the geographical constraints imposed by the tenant's regulatory environment. You are looking for evidence that the provider's monitoring of their global infrastructure ensures compliance with localized data protection laws, while maintaining the integrity of their overarching security strategy. Effective auditing requires verifying the cryptographic implementation validity and ensuring that key management strategies are sufficiently granular to provide the tenant with the necessary control over their data lifecycle. By aligning your assessment with the ISO standards, you create a repeatable methodology that allows you to report deficiencies with authority and track remediation efforts in a way that is meaningful to stakeholders. This structured approach is what differentiates a high-level review from a true, deep-dive cloud audit that provides genuine risk mitigation. See you in the next lecture. Welcome back. Today we address the complex task of mapping global regulatory requirements to the technical realities of cloud environments. When we approach regulatory compliance in the cloud, the primary challenge is translating abstract legal mandates into concrete, observable system controls. Regulations like GDPR, HIPAA, or the PCI DSS are often written with traditional on-premises data centers in mind. Yet they must be adapted to the elastic, virtualized nature of modern cloud services. As auditors, our objective is to bridge this gap by aligning control objectives from the CSA Cloud Controls Matrix with the specific technical implementation of the cloud provider. We do not simply check for the existence of a document. We look for evidence that a control, be it administrative, technical, or operational, is actively functioning within the provider's infrastructure. This mapping process requires a rigorous understanding of the shared responsibility model, which serves as the foundation for determining who is accountable for a specific compliance state. If we fail to accurately delineate these boundaries, we risk overlooking critical gaps in our audit scope, which is a common failure point in certification examinations. Systematically evaluating these mappings involves a deep dive into the underlying architecture of the tenant's environment and the provider's attested controls. We focus on evidence gathering by correlating high-level requirements with specific technical configurations, such as identity and access management policies, encryption standards, and network segmentation. For instance, consider the requirement for data residency under GDPR. An auditor must look past the provider's general privacy policy to verify the actual configuration of data storage buckets and the geographic pinning of processing workloads. This level of granularity necessitates analyzing vendor-independent attestation reports, such as Type 2 SOC reports or ISO 27017 certifications, to understand the provider's baseline compliance. We must also verify that these controls hold up under the dynamic nature of cloud operations, including automated provisioning workflows and the rapid scaling of resource pools. A static snapshot of a system configuration is rarely sufficient, as the ephemeral nature of microservices or containerized workloads demands a shift toward continuous compliance monitoring. Effective compliance mapping also demands that we scrutinize the intersection of risk management and third-party supply chain dependencies. In a hybrid or multi-cloud environment, the complexity of these mappings increases exponentially because we are essentially dealing with multiple overlapping layers of responsibility. We evaluate whether the controls implemented, such as key management strategies or incident response forensic readiness, are consistent across all platforms. It is not enough to confirm that encryption is enabled. We must validate the cryptographic implementation, ensuring that the key management lifecycle satisfies regulatory requirements for data protection. When evaluating these diverse environments, we rely on automated assessment tools to provide the visibility needed to track compliance status in real time. This methodology allows us to identify deficiencies early in the development lifecycle and implement remediation plans before a formal audit occurs. Success in this area is characterized by the ability to demonstrate that the organization has maintained an objective and independent posture while navigating the inherent uncertainties of distributed cloud systems. See you in the next lecture. Welcome back. Today, we are shifting our focus to the practical realities of gathering and preserving compliance evidence within highly dynamic cloud environments. When we transition from traditional data centers to ephemeral cloud infrastructures, we quickly realize that our audit work must evolve. In a physical environment, we might walk through a server room or inspect hardware serial numbers. But in an abstracted cloud environment, physical proximity is irrelevant. Instead, We rely on logs, configuration files, and state snapshots provided through application programming interfaces. The challenge here is the ephemeral nature of these components. A container might only exist for a few minutes to process a specific request before being destroyed to save costs. If your audit process relies on manual point-in-time snapshots, you will inevitably miss the vast majority of the control activity occurring within the environment. Therefore, the auditor must shift toward evidence collection that is integrated directly into the infrastructure as code pipeline or through immutable log aggregation services. To evaluate the effectiveness of controls, we align our assessment criteria with the Cloud Security Alliance Cloud Controls Matrix and the Consensus Assessments Initiative Questionnaire. These frameworks provide a structured way to map technical, operational, and administrative controls to the shared responsibility model. When you examine a cloud service provider, you must clearly distinguish between the provider's native security controls and the tenant's configuration responsibilities. The provider might secure the hypervisor and the underlying physical storage, but the tenant remains responsible for identity and access management, data classification, and encryption key management. Ignoring this delineation leads to audit findings that are unenforceable or, worse, misaligned with the actual risks. You are effectively auditing the tenant's ability to leverage the provider's native capabilities to meet specific regulatory requirements. Evidence gathering in this context requires a strategic mix of automated assessment tools and manual review of independent attestation reports. You cannot manually inspect every microservice deployment, so you should prioritize checking the security validation steps embedded in the CI/CD pipeline. These automated gates often serve as the strongest piece of evidence that a control is being applied consistently. Simultaneously, you must review the provider's SOC 2 or ISO 27001 reports to obtain bridge letters or independent validation of the controls the provider manages on your behalf. This vendor-independent attestation is crucial for supply chain risk management, especially when the infrastructure spans multiple cloud service providers. Your goal is to construct a continuous chain of evidence that proves the state of the security controls at any given moment in time. Data sovereignty and jurisdictional requirements add another layer of complexity to the auditing process. You must be able to prove, with cryptographic certainty, exactly where data resides and which entities have access to it at any point. This necessitates an audit of the cloud provider's regional deployment configurations and the specific access policies enforced through your chosen IAM solution. When conducting these assessments, look at the audit trails for encryption key usage, as these often reveal unauthorized access attempts that would otherwise remain hidden. By auditing these logs against established performance metrics and service-level agreements, you can identify deficiencies in incident response capabilities before they manifest as security breaches. This proactive identification is the hallmark of modern, continuous audit practice in a hybrid or multi-cloud architecture. Always remember that, as an auditor, your independence remains your most valuable asset when reporting these findings to the business. You must bridge the gap between technical reality and business strategy by translating raw log data into risk-based narratives. If you find that the automated patching of container workloads is insufficient, you must frame this not just as a missing update, but as a risk to the availability and integrity of the entire service stack. This helps stakeholders understand the remediation effort required and ensures that the audit output leads to tangible architectural improvements. By aligning your assessment with these broader organizational goals, you transform the compliance function from a hurdle into a reliable mechanism for resilience. I will see you in the next lecture. Hello, and welcome back. In this lesson, we will explore the core principles of architecting and auditing robust identity and access management solutions within complex cloud environments. Identity and access management sits at the very heart of cloud security, essentially replacing the traditional perimeter-based defense with a focus on individual identity. When we talk about IAM in the cloud, we are moving away from network-centric trust models toward an architecture where every access request is subject to verification. Implementing the principle of least privilege is mandatory here, which means we must grant entities exactly the permissions required for their specific tasks and absolutely nothing more. This concept is fundamental to the zero trust maturity model, which assumes that no internal or external network is inherently trustworthy. In a practical cloud auditing context, we must evaluate whether these identity configurations are dynamic or static. as the agility of cloud resources demands automated, granular policy enforcement. We should also examine the implementation of federated identities, which allow organizations to manage identities across multiple domains without duplicating credentials. This is closely related to single sign-on protocols, which streamline user experience while centralizing the audit trail for security teams. When assessing these systems, you are not just looking at a configuration file. You are validating that the governance over the identity lifecycle, from provisioning to deprovisioning, is logically sound and operationally effective. To effectively audit these systems, we need a rigorous approach that goes beyond ticking boxes on a compliance checklist. Your evaluation criteria should be deeply aligned with the Cloud Security Alliance Cloud Controls Matrix and the CAIQ framework, which provide an industry-standard lexicon for assessing technical, operational, and administrative controls. Think of the ISACA CCKK perspective as a bridge between pure architectural design and the audit rigor required to prove that security works continuously, not just once a year. When we evaluate provider versus tenant obligations in the shared responsibility model, it becomes clear that while the cloud provider manages the underlying identity service infrastructure, the tenant is responsible for the actual identity governance and group assignments. You need to gather evidence that demonstrates how the tenant manages their user permissions and whether they are utilizing appropriate multi-factor authentication mechanisms consistently across the entire organization. Relying on vendor-independent attestation reports like SOC2 is helpful, but as an auditor, you must verify the specific settings within those environments to ensure the tenant has correctly mapped their control objectives to the technical implementation. This is particularly important in hybrid and multi-cloud scenarios, where identity sprawl can lead to significant blind spots if not carefully managed through centralized orchestration and rigorous validation of access paths. Effective auditing requires a deep dive into the operational lifecycle of identities, especially when dealing with privileged access management, which is a high-risk area for any organization. We must evaluate whether privileged accounts have adequate monitoring and whether they utilize just-in-time elevation, which drastically reduces the window of opportunity for an attacker to gain persistent access. You will also look for evidence of automated provisioning and deprovisioning processes, as manual management in a virtualized, elastic environment is prone to human error and orphan account accumulation. The validation process involves probing the effectiveness of these controls by checking for the presence of documented policies that are actually enforced within the identity provider. Furthermore, consider the audit trail itself. A robust IAM solution must provide immutable, comprehensive logs that record who accessed what, when, and from where. In an audit, you should request those access logs to perform a sanity check against the established baseline policies. If the organization claims to be using zero trust principles, your evidence gathering must confirm that there are mechanisms for periodic reauthentication and that access rights are scoped narrowly according to the actual current requirements of the business workload. Maintaining objective independence while using automated assessment tools is a critical nuance of the modern cloud auditor's role. Many cloud platforms provide native security posture management tools that can continuously monitor for misconfigured identity roles, such as an S3 bucket with broad public read access or a service principal with excessive administrative rights. As an auditor, your task is to understand how these tools are configured, what alerts they trigger, and how the organization ensures that these alerts are addressed in a timely fashion. You are effectively shifting from a point-in-time review to an assessment of the organization's continuous assurance capabilities. Vulnerability management in this context extends to identifying identity-related misconfigurations that could serve as a foothold for an attacker, even if the underlying workload itself is patched. This approach ensures that you align business and IT strategies, ensuring that identity management supports agility while maintaining an uncompromising security posture. By focusing on these granular control objectives and the efficacy of the automated detection and remediation cycles, you demonstrate the competence necessary to navigate the complexities of contemporary distributed cloud systems. See you in the next lecture. Welcome back. In this lecture, we will explore the security requirements for decentralized microservices and the auditing standards necessary to govern them effectively. Microservices architecture shifts the security perimeter from a monolithic boundary to the individual service level, which requires a fundamental rethink of audit procedures. When auditing these distributed systems, your primary objective is to verify that security controls are consistently applied across heterogeneous service environments rather than concentrated at the network edge. You must evaluate how authentication and authorization are handled for inter-service communication, as the traditional model of relying on network-level trust is insufficient in a microservices deployment. If developers rely on internal network trust to move data between services, they introduce a critical vulnerability where any compromised component could potentially traverse the entire application stack. Instead, you need to look for evidence that every service validates the identity and permissions of any entity requesting its resources, typically implemented through mutual transport layer security or token-based authentication, such as JSON Web Tokens. Furthermore, the use of a service mesh becomes a significant point of interest for an auditor because it abstracts the logic for traffic management, encryption, and telemetry away from the application code. You should examine how the service mesh enforces MTLS policies, as this provides the technical control needed to ensure data in transit is encrypted even within a private cloud network. The complexity of microservices naturally leads to a reliance on API gateways as the centralized entry point for all external traffic. Your audit methodology should prioritize the effectiveness of these gateways in enforcing rate limiting, request validation, and coarse-grained authentication before any request reaches the backend services. From an operational perspective, you must confirm that the gateway acts as a robust gatekeeper that prevents unauthorized or malformed requests from infiltrating the ecosystem. When assessing these components, check if the gateway configuration is managed as code and whether there is an immutable record of changes that allows for reproducible audit logs. Beside the gateway, the visibility of inter-service traffic is essential not just for performance, but for identifying potential exfiltration or lateral movement. Distributed application tracing is the mechanism that provides this visibility, allowing you to audit the path of a request across dozens of potential service dependencies. If an organization lacks these tracing mechanisms, they lose the ability to perform forensic analysis in the event of a security incident, making it impossible to satisfy the traceability requirements of the CSA Cloud Controls Matrix. Data protection within a microservices architecture demands a granular approach to encryption and key management that defies the simple perimeter strategies of the past. When evaluating the security of these workloads, you should verify that developers are not hard-coding sensitive information or cryptographic keys within container image definitions or environment variables. Instead, check for the utilization of centralized, secure vault solutions that provide dynamic secret injection at runtime, ensuring that if one service is compromised, the keys remain isolated. This strategy aligns with the principle of least privilege, as each service should only possess the specific keys required for its immediate function, rather than having access to a global encryption secret. You must also validate the data sovereignty requirements, as microservices are often distributed across multiple geographical zones to improve latency and resilience. If a specific service is processing PII or sensitive data, you need to ensure that the audit logs confirm the geography of data storage and processing, matching the regulatory requirements defined in the initial risk assessment. Continuous auditing principles are most effective when applied to the automated delivery pipelines that underpin microservices. As an auditor, your role involves validating that the security controls which are effective during internal testing remain effective in production after rapid deployment cycles. This means you should review the integration of automated security testing, such as vulnerability scanning of container images in the CI/CD pipeline, to prevent known threats from reaching the runtime environment. Focus your evaluation on the remediation tracking process, specifically how the organization demonstrates that identified vulnerabilities and microservice dependencies are addressed within established service-level agreements. Without a tight feedback loop between the automated scanner and the development team, the risk mitigation strategy effectively breaks down, leaving the architecture vulnerable to supply chain attacks. You must treat the entire software supply chain as an audit target, reviewing the attestations of open-source libraries and container-based images used within the services to ensure they meet your internal governance standards. Finally, ensure your report focuses on the shared responsibility model, as it applies to the underlying infrastructure management of the microservices. While the provider remains responsible for the security of the underlying orchestrator, the audit must confirm the tenant's responsibility for securing the container configuration and the communication logic that resides above the orchestration layer. Your assessment should conclude with a clear picture of whether the tenant is correctly managing the administrative controls, such as logging access to the Kubernetes API server and ensuring that audit logs are shipped to a protected, centralized location. By focusing on these technical and operational realities rather than just high-level policy, you provide the rigor necessary to validate the resilience of a modern hybrid multi-cloud architecture. See you in the next lecture. Welcome back. Today, we address the technical and administrative nuances of Docker container security. When we approach the security of Docker containers, we must fundamentally shift our perspective from protecting static virtual machines to securing ephemeral runtime environments. Unlike traditional virtualization, where each guest operating system carries its own kernel, Docker relies on the host kernel to manage resource isolation. This shared kernel architecture creates a significant attack surface because any vulnerability in the kernel itself could potentially compromise all containers running on that specific host. Consequently, an auditor must first examine the hardening state of the host operating system, specifically looking for outdated kernel versions or unnecessary modules enabled by default. Furthermore, we must evaluate the configuration of the Docker daemon itself, as it frequently runs with elevated privileges that pose a massive risk if accessed by an unauthorized process. Audit criteria should reflect the least privilege principle, ensuring that the daemon is restricted and that user namespaces are utilized to map container root to non-privileged host users. Moving from the host to the images themselves, the supply chain risk in a containerized environment is often the most overlooked component of an audit. Images are typically constructed from layers sourced from public registries, which might contain deprecated libraries, hidden backdoors, or outdated binaries with known common vulnerabilities and exposures. An effective audit must verify the existence of an automated image scanning process that triggers upon a pull request or a commit to the registry. You should look for evidence that developers are using signed base images and that there is a strict policy in place to block the deployment of any image exceeding a predefined vulnerability severity score. It is not sufficient to simply perform an initial scan. Images must be continuously reevaluated, as a library that is secure today may develop a critical vulnerability by tomorrow. This practice aligns directly with the requirement for continuous monitoring and vulnerability management, as codified in the Cloud Security Alliance Cloud Controls Matrix. Runtime protection and isolation techniques represent the third pillar of our assessment, necessitating a deep dive into how containers interact with the host and each other. By default, Docker containers do not provide the same levels of strict security boundaries as traditional virtual machines unless specific constraints are actively applied. During an engagement, check for the implementation of Linux control group limits, which prevent a single container from consuming all host CPU or memory resources, effectively mitigating primitive denial of service attempts. You should also audit the usage of SecOps profiles and AppArmor or Selinux policies, which restrict the system calls a container process can make to the host kernel. If these security modules are disabled or kept at default settings, the container breakout risk increases substantially, potentially allowing an attacker to traverse the network or elevate privileges to the host level. Documentation of these configurations provides the evidence necessary to validate that your security architecture is not merely theoretical, but operationally effective. Finally, we must integrate these technical findings into the broader context of organizational governance and the shared responsibility model. While the cloud provider manages the underlying infrastructure, the tenant remains entirely responsible for the security of their containerized applications, their data, and their configurations. Your role as an auditor is to verify that these lines of responsibility are mapped clearly within the organization's policies and that there is an active process for gathering evidence of control effectiveness. This includes reviewing logs for container lifecycle events, assessing the secret management strategies to ensure sensitive production credentials are not stored in image layers, and testing the response capabilities of the security team. When reporting deficiencies, you must distinguish between risks inherent to the technology stack and those that stem from a failure in administrative oversight during the development cycle. Ensuring that container security validation processes are built into the DevSecOps pipeline acts as the primary mechanism for maintaining the resilience of your hybrid or multi-cloud architecture. See you in the next lesson. Welcome back. In this session, we investigate the specific requirements for hardening a Kubernetes cluster within a cloud environment. When we talk about Kubernetes cluster hardening, we are essentially moving the goalposts from traditional perimeter defense to a model that assumes the infrastructure is inherently dynamic and potentially compromised. As auditors, we cannot simply look at a firewall configuration and call it a day, because in a containerized world, the network boundaries are defined by software-defined networking and ingress controller logic. The core objective here is to limit the blast radius of any individual component by adhering to the principle of least privilege. We start by examining the control plane, which acts as the brain of the cluster, and ensure that access to the API server is restricted through robust authentication and authorization mechanisms. If the API server is exposed to the public internet without proper mutual TLS or OIDC integration, the entire cluster integrity is forfeit, regardless of how well the worker nodes are patched. Hardening here means confirming that anonymous authentication is disabled and that audit logging is enabled to track every single request made to the cluster interface. Moving down the stack, we must evaluate how the cluster manages communication between pods, which is where network segmentation becomes the primary control. By default, most Kubernetes networking models allow pods to communicate freely with one another across the entire cluster namespace, which creates significant risk for lateral movement during a security breach. An auditor should look for the implementation of network policies that operate at layer 3 or layer 4 to explicitly allow only legitimate traffic flows. You are essentially looking for an allow list approach where everything is denied by default, and developers must define specific rules for necessary service-to-service interaction. We verify this by reviewing the manifest files and the runtime state of the network provider settings, looking for evidence that segmentation is enforced rather than just proposed. Without these granular controls, a vulnerability in a single public-facing web microservice could lead to an attacker gaining control over sensitive backend database pods without ever hitting a secondary perimeter defense. Role-based access control, or RBAC, is another pillar where the configuration often deviates from institutional best practices during the rapid scaling phase of cloud development. Frequent audit findings reveal service accounts that have been granted cluster-wide privileges simply because the application team did not want to spend time defining specific permissions for a particular task. As auditors, we must scrutinize the cluster role and cluster role binding resources to identify overly permissive accounts, especially those with verbs like delete, patch, or escalate over critical system resources. It is not sufficient to simply check if RBAC is enabled. We must evaluate the actual mapping of identities to privileges and ensure that the administrative surface area is kept as small as is operationally feasible. We should also investigate how those identities are managed, checking if the cluster integrates with external identity providers or if it relies on static tokens that are difficult to rotate and monitor. In the context of the CCAK framework, this is evidence of proactive risk mitigation rather than reactive security patching. The management of secrets represents one of the most common failure points in Kubernetes environments, as developers often mistakenly store sensitive credentials directly in plain text within configuration files or environment variables. An auditor must verify that the organization leverages native secret objects stored in etcetcd, but more importantly, that these are backed by a robust encryption at rest strategy using a key management service or an external vault solution. If the secret data is not encrypted at the etcd level, anyone with access to the cluster backing store can easily extract service account tokens, database passwords, and API keys. We also look for evidence of volume-level mounting for secrets rather than environment variable injection, as environment variables are often logged or exposed in process dumps that can be scraped by unauthorized actors. Confirming whether the cluster uses automatic secret rotation or if there is a documented process for lifecycle management completes the check for this control objective. By ensuring that secrets are treated as transient, encrypted resources rather than static configuration data, we meet the rigorous standards of modern cloud-native security auditing. See you in the next lecture. Welcome back. Today we examine how security integrates directly into the continuous integration and deployment pipelines within a cloud environment. When we shift security left into the software development lifecycle, we move from reactive patching to proactive prevention. In a traditional environment, auditing often occurred after a system reached production, but in a DevOps model, this approach is insufficient. We must treat security as code, meaning that every configuration, policy, and control is versioned and automated. By embedding security gates directly into the CI/CD pipeline, we ensure that no code reaches an environment without passing automated vulnerability scans and compliance checks. This shift requires that auditors understand the underlying tooling, such as static application security testing and dynamic analysis suites, that populate the audit trail automatically. The goal is to provide continuous assurance rather than point-in-time validation, which is a fundamental requirement for the CCAK examination. To evaluate these pipelines effectively, an auditor must look for objective evidence of control effectiveness. We start by examining the configuration of build servers and the integrity of the build artifacts themselves. Does the pipeline include secret management to prevent hard-coded credentials from entering the codebase? We must review how these secrets are accessed, rotated, and monitored within the service mesh or container orchestrator. Beyond functional security, the auditor must verify that administrative access to the deployment pipeline follows the principle of least privilege. If a developer can bypass a security gate or modify the build logic, the integrity of the entire chain is compromised. These institutional controls are just as critical as the technical implementation of encryption or firewall rules. Managing vulnerabilities within a containerized or microservices architecture presents unique challenges that traditional audits often miss. We look for evidence that vulnerability management extends throughout the container registry and into active production workloads. If a vulnerability is detected, what is the defined remediation SLA, and how is it tracked to closure? Auditors need to review the reporting phase to ensure that identified deficiencies are presented to management in a way that aligns with business and IT strategies. We are not just looking for a list of bugs, but for a systemic approach to risk mitigation that covers the entire life cycle of a container, from its image creation to its eventual retirement. This requires verifying that the pipeline includes automated compliance validation against frameworks like the CSA Cloud Controls Matrix. Third-party supply chain risks remain a significant concern in these automated environments, particularly when integrating open-source components. We must evaluate how the organization vets third-party dependencies before they are allowed into the build pipeline. Does the team employ software composition analysis to identify known vulnerabilities in libraries? If a vendor provides a library, do we have an independent attestation report to verify its security posture? As auditors, we must map these external controls back to the tenant's responsibility under the shared responsibility model. We must ensure that the organization does not blindly trust third-party software, but instead validates the security of those components as part of their own internal compliance governance. Finally, let us consider the requirement for maintaining objective independence while utilizing automated assessment tools. Using a tool does not absolve the auditor from needing to understand the underlying architecture and the logic of the checks being performed. We must verify that the automated tools are correctly configured to match the security objectives of the enterprise. If the tools report success, we need to inspect the logs and evidence to ensure that these results are not a false positive or a misinterpretation of a metric. Accurate reporting requires a deep understanding of cryptographic implementation validity and how identity and access management policies are enforced across the distributed infrastructure. By maintaining this rigor, the auditor provides the assurance needed to satisfy both internal stakeholders and external regulatory bodies. I will see you in the next lecture. Welcome back. Today we are going to explore the critical domain of securing infrastructure as code. Infrastructure as code, or EEC, is the practice of managing and provisioning computer data centers through machine-readable definition files rather than physical hardware configuration or interactive configuration tools. When we view this through the lens of an ISACA auditor, we must recognize that the shift from manual provisioning to automated templates introduces both significant efficiency gains and unique security risks. The core problem is that a misconfiguration in a script is no longer a localized issue, but a systemic vulnerability that can be replicated across an entire cloud environment instantly. Auditing EEC requires us to move beyond traditional manual checklists and instead verify the controls that govern the lifecycle of these templates. You should consider the template file itself as the source of truth for the entire infrastructure architecture. If the template defines an S3 bucket as public, the infrastructure will be public. If the template lacks encryption parameters, the resulting service will lack encryption at rest. The primary objective when assessing EEC is to ensure that secure defaults are baked into the provisioning process rather than bolted on after deployment. We achieve this through static analysis, where tools scan Terraform files or CloudFormation templates for prohibited patterns before they are ever applied to a production environment. An effective audit must evaluate whether the organization uses these automated scanners as a mandatory quality gate within their deployment pipeline. We are looking for evidence that security policies, such as mandatory tagging, restrictive network security groups, and encryption at rest configurations, are technically enforced. If a developer can bypass these checks, the control fails the requirement for effective risk mitigation. You need to verify that there is a documented process for exception management when these automated rules are triggered during a deployment. Immutable infrastructure is a central concept here, as it dictates that once a service is deployed, it should not be modified in place. Instead of patching a running server or updating a live load balancer, we update the EEC template and redeploy the entire stack. From an audit perspective, this simplifies many compliance requirements because the state of the infrastructure is predictable and version controlled. We can compare the current running state against the version controlled template to detect drift, which is a significant indicator of unauthorized change. When auditing this, your evidence gathering should focus on the integrity of the Git repositories where these templates are stored. You must confirm that access to modify these scripts is strictly limited, properly authorized, and logged through an audit trail that shows exactly who changed which line of code. You must also reconcile these technical practices with the shared responsibility model, as the cloud service provider maintains the underlying platform while the tenant controls the configuration defined in the templates. The auditor has to verify that the tenant understands which security controls are their responsibility to define within their EEC code. For example, while AWS handles the physical hardware of a database service, the encryption configuration and the network access control lists are entirely the tenant's responsibility. If an auditor finds that sensitive data is stored in an unencrypted database, pointing to the provider's SLA is insufficient if the audit reveals the flaw originated in the tenant's EEC configuration. Your report should clearly distinguish between provider-managed security and tenant-managed security within the scope of the infrastructure definition. This distinction is vital when performing jurisdictional data sovereignty assessments, as the placement of resources is determined by the region variables in your EEC templates. Finally, we must evaluate the resilience of the entire DevSecOps pipeline as it relates to supply chain risks. Many organizations utilize third-party modules or community-sourced templates to speed up infrastructure deployment, which creates an implicit trust dependency. An audit program must verify that these external dependencies are scanned for vulnerabilities before they are integrated into the internal codebase. We are essentially looking for a verification process that treats infrastructure code with the same rigor as application source code, including mandatory code reviews and cryptographic signing. The audit must demonstrate that the organization has an incident response and forensics capability capable of tracing a security incident back to the specific IEC template revision that created the vulnerable state. This creates a closed loop where policy requirements are mapped directly into code, audited for effectiveness, and continuously monitored for drift. See you in the next lecture. Welcome to this exploration of how auditing shifts when moving from traditional on-premises environments to the cloud. We will examine the core differences and methodologies required to maintain rigorous standards in virtualized infrastructures. In a traditional audit, the perimeter is tangible and often static. You walk into a data center, check the cage locks, verify the physical hardware serial numbers, and observe the environmental controls directly. When you transition to the cloud, this physical access is abstracted away and effectively managed by the cloud service provider. You are no longer auditing the physical cable routing or the HVAC redundancy, but rather the control plane and the configuration of abstracted services. This shift means the auditor must move from a site visit mentality to a data-driven verification approach. The control objectives remain largely the same, but the evidence gathering technique transforms from manual observation to programmatic API interrogation. You must trust that the provider's independent attestation reports, such as SOC or ISO documents, cover the physical layer, allowing you to focus your professional skepticism on the logical implementation within the tenant environment. Effective cloud auditing requires a deep understanding of the shared responsibility model as the bedrock of your assessment. While the provider owns the security of the cloud, you are responsible for security in the cloud, which includes configuration, data protection, and identity management. Evaluating these areas requires familiarity with frameworks like the CSA, CCM, and the CAIQ, which provide the mapping between control objectives and cloud-native technical implementations. When reviewing your environment, you must determine if your technical, operational, and administrative controls are configured to satisfy these frameworks despite the lack of direct physical control. For instance, in an IaaS setup, you are responsible for patching guest operating systems, whereas in a SaaS environment, that duty often shifts entirely to the vendor. Your audit plan must clearly delineate these boundaries to avoid redundant efforts or, more dangerously, gaps where neither party claims responsibility for a specific control. Moving beyond the boundaries, the audit must address the dynamic nature of cloud-native components like microservices and containerized workloads. Traditional audits might look at a static server configuration once a year, but a cloud-based audit recognizes that infrastructure often changes via CI/CD pipelines and infrastructure as code templates. Your assessment strategy must incorporate automated tools that continuously validate the state of the system against your desired security posture. This is where continuous auditing principles become vital because a configuration drift occurring after an annual audit could lead to significant data exposure. You should be reviewing logs, checking identity and access management policies for least privilege violations, and validating the implementation of encryption for data at rest and in transit. By automating these checks, you move from a point-in-time snapshot to a persistent monitoring capability that better reflects the reality of a distributed environment. Vendor-independent attestation is another cornerstone, particularly when dealing with third-party supply chain risks and complex multi-cloud architectures. You cannot expect to perform on-site audits of massive global providers, so you must become adept at reading and interpreting Type 2 SOC reports and other third-party security assessments. This involves checking the scope of the auditor's opinion to ensure it covers the specific cloud services you are utilizing. Furthermore, you must reconcile these reports with your own internal compliance needs, mapping the provider's stated controls to your business requirements. This gap analysis is where you prove your value as an auditor by translating technical attestation into meaningful risk management reports for your stakeholders. It is not about verifying every underlying component, but rather about confirming that the provider's controls are effective and aligned with the service level agreements you have signed. Finally, ensure that your audit documentation reflects the shift toward logical and procedural evidence. When dealing with encryption, it is insufficient to simply ask if data is encrypted. You must verify that the cryptographic key management strategy is robust and that keys are stored in a secure, isolated manner. For incident response and forensics in the cloud, verify that the necessary logging levels are active and that those logs are transmitted to a persistent, immutable storage location. You are effectively shifting your rigor from physical verification to the validation of automation in logical configurations. By maintaining this objective independence and using modern tooling, you ensure that your audit results are defensible, accurate, and provide a clear path for remediation in the event of an identified deficiency. These capabilities distinguish a competent cloud auditor from those still attempting to apply legacy audit procedures to essentially ephemeral, virtualized assets. Talk to you in the next lesson. Welcome back to our journey through the complexities of cloud auditing. In this session, we will examine how to transition from static, time-bound audits to the dynamic world of continuous auditing. Traditional auditing relies on periodic snapshots of a system's state, often collected through manual evidence gathering that is usually obsolete by the time the auditor reviews it. In the cloud, this approach is insufficient because the infrastructure is ephemeral and changes occur at the speed of software deployment. Continuous auditing leverages cloud-native APIs and real-time telemetry to transform the audit function from a reactive process into a proactive mechanism of perpetual assurance. By integrating compliance as code frameworks into the development pipeline, we can define our control objectives as machine-readable policies that automatically validate system configurations against security benchmarks. This allows organizations to move beyond mere compliance checklists and instead verify that operational, technical, and administrative controls are functioning as intended at any given second. The goal is to establish a rigorous, repeatable mechanism that provides objective evidence of the cloud environment's security posture without requiring the heavy lift of manual periodic evidence requests. To implement this successfully, we must first map our control objectives to the CSA Cloud Controls Matrix and the CAIQ frameworks, ensuring that our automated tests align with industry-recognized security requirements. When we talk about technical controls in a continuous auditing context, we are primarily concerned with the programmatic inspection of resources. For example, we might employ services like AWS Config or Azure Policy to identify non-compliant storage buckets that are publicly accessible or instances that lack valid security group protections. These tools emit events in real time, enabling immediate alerts when a configuration drift occurs, which aligns with the incident response and remediation tracking requirements of the ISACA CCAK curriculum. By maintaining this constant stream of telemetry, auditors gain the ability to evaluate the effectiveness of controls not just on a sample basis, but by observing the entire population of resources over time. This architectural shift ensures that security validation is inherent to the infrastructure rather than an afterthought applied at the end of a fiscal quarter. Beyond configuration management, continuous auditing must also address the complexities of identity and access management and data protection strategies. We need to verify that encryption keys are being managed according to best practices and that access policies adhere to the principle of least privilege, which is frequently challenged in highly dynamic multi-cloud architectures. This requires auditing the validity of cryptographic implementation by programmatically checking if, for instance, an RDS instance has enabled transparent data encryption, or if an S3 bucket utilizes the appropriate KMS key, rather than relying on a vendor's attestation alone. Furthermore, in microservices and container-based environments, we must audit the registry and the orchestration layer to ensure that only verified images are deployed to production clusters. This requires integrating compliance validation into our DevSecOps pipelines, ensuring that every deployment represents a known and secure state, preventing the proliferation of shadow IT or improperly configured services that could lead to data leakage. Finally, we have to recognize that continuous auditing is fundamentally about maintaining visibility into the shared responsibility model. While cloud service providers offer a broad range of native toolsets for introspection, the tenant remains responsible for the configuration of these services and for the data residing within them. Consequently, our audit methodology must remain independent, using automated assessment tools to bridge the gap between what the provider declares as secure and what is actually implemented in the tenant-specific context. This includes monitoring service-level agreements to ensure that operational performance meets business requirements, as well as mapping regulatory compliance across various jurisdictions to handle data sovereignty concerns. By planning for, executing, and reporting on these automated flows, we mitigate third-party supply chain risks and ensure that hybrid, multi-cloud architectures remain resilient against threats. This structured approach to evidence collection and remediation tracking is the hallmark of a mature cloud governance strategy, proving that you have the competence to audit highly distributed and virtualized environments with traditional rigor. See you in the next lecture. Welcome back, and let's dive into the practical realities of assessing cloud service provider transparency. Transparency in a cloud environment is not merely about access to a dashboard. It is a systematic requirement to verify that the service provider's operational reality matches their contractual and security claims. When we audit a provider, we must rely on a hierarchy of evidence that begins with independent attestation reports, such as SOC 2 or CSA star certifications, which provide a snapshot of control effectiveness validated by a third party. However, these documents are point-in-time assessments, and as an auditor, you must complement them with continuous monitoring data derived from the provider's portal metrics. These metrics offer real-time visibility into the health of the infrastructure, latency, and security events, which are essential for validating the operational status of technical, administrative, and physical controls. Your task is to map these findings specifically against the controls documented in the CSA Cloud Controls Matrix, ensuring that the evidence you collect directly addresses the requirements of the CAIQ framework. For instance, if a provider claims robust identity management, you should look beyond their policy document and request tangible evidence of multi-factor authentication implementation rates or privileged access activity logs. It is common for providers to offer varying levels of transparency, and your assessment criteria must hold them accountable for providing the necessary artifacts to support their security assertions. By applying traditional audit rigor to these dynamic feeds, you can bridge the gap between abstract service level agreements and actual delivery performance. When evaluating transparency, the concept of the shared responsibility model remains your primary guide for delineating what is verifiable on the provider's side versus the tenant's side. You cannot simply accept a provider's high-level security summary. You must drill down into how they manage the underlying isolation mechanisms, such as microservices segmentation or container orchestration, that form the backbone of their offering. If the provider uses a shared cloud architecture, your audit focus must shift to how they manage logical segmentation and whether they provide adequate transparency regarding their vulnerability, management, and patching cycles. Inadequate transparency is frequently a precursor to compliance drift, particularly in multi-cloud or hybrid environments where data might traverse multiple jurisdictions. Consequently, your assessment methodology should include a review of the provider's data sovereignty policies, ensuring that the geographical footprint of their services aligns with your legal and regulatory obligations. You must evaluate how incident response information is communicated to the tenant, as an opaque communication channel during a security breach is a significant operational failure. Even when automated tools provide high-level summaries, verify that these tools are not masking underlying configuration weaknesses. True transparency means having a clear, auditable trail that links specific control objectives to the technical configurations in place, allowing you to confirm that the provider's security architecture is not just a marketing claim, but a functional reality of their service delivery. Effective evaluation also entails tracking remediation efforts when transparency gaps are identified in the provider's systems. If you notice that an attestation report highlights a design deficiency, you must query the provider's remediation tracker to understand how they intend to mitigate that exposure. Failing to demand this level of detail essentially abdicates your governance responsibility, as you remain accountable for the data you host within their environment, regardless of the provider's limitations. Furthermore, be wary of transparency theater, where providers supply excessive amounts of irrelevant data to distract from deeper security concerns. Your audit strategy should prioritize actionable intelligence over volume, utilizing risk-based sampling to verify the validity of encryption key management and data protection strategies. If a provider claims they support bring your own key functionality, verify the transparency of their key lifecycle management processes to ensure you retain control over your data's cryptographic integrity. Remember that your goal is to validate the effectiveness of controls through a disciplined, evidence-based approach that does not allow the complexity of virtualization to obscure basic security principles. As you move forward, keep these methodologies focused on maintaining objective independence so that your audit findings remain defensible against regulatory scrutiny and internal stakeholders. I look forward to discussing how these practices apply to contract analysis in the next session. Welcome back. In this session, we will examine the critical process of auditing service-level agreements to ensure they align with your organization's operational requirements. When we approach the audit of a service-level agreement, or SLA, we are not simply reading a contract to check for legal presence. Instead, we are performing a technical and operational validation of the service provider's commitments against your enterprise's continuity needs. You must first look at the uptime guarantees, which are often expressed as a percentage of availability. A common pitfall is assuming that a 4-nines promise automatically maps to your business requirements without accounting for the definition of downtime. Audit rigor requires you to investigate how the provider defines an outage and whether that definition excludes scheduled maintenance or specific incident types that might actually leave your business non-functional. By examining the baseline performance metrics, you translate abstract percentages into tangible operational realities. This stage of the audit is where you determine if the provider's technical commitments in the SLA documentation provide sufficient cover for your specific workload's tolerance for disruption. Beyond simple uptime, the assessment must pivot towards support metrics and the specific mechanisms of incident response. An auditor needs to confirm that response time targets are not just stated as aspirations, but are backed by formal operational procedures. You should ask to see how the provider measures these intervals and whether they include human-in-the-loop validation for incident closure. Furthermore, verify whether the SLA includes provisions for transparency during service degradation, such as status page accuracy and historical reporting. If the contract lacks clear penalties or service credits for failure to meet these metrics, the SLA effectively lacks teeth, which is a significant finding in any audit report. You are essentially looking for an alignment between the provider's service delivery capabilities and the controls your enterprise requires to maintain its own compliance posture. Evaluating these administrative controls requires you to map the provider's obligations directly against your internal business continuity plans. We must also consider the role of the shared responsibility model when scrutinizing these legal instruments. It is a frequent mistake to assume that an SLA covering security implies that the provider takes full responsibility for all security outcomes. Your task as an auditor is to isolate what is strictly the provider's domain, such as physical infrastructure availability, from the tenant's responsibility, such as identity and access management configuration. If your internal team misconfigures a security group, the SLA uptime guarantee remains valid, but your service remains insecure, which illustrates why this distinction is vital. You should look for language within the contract that clarifies these boundaries and identifies where jurisdictional or data sovereignty requirements are addressed. Since auditors often deal with multi-cloud environments, ensuring that these agreements are consistent across different vendors is a significant challenge. You must verify that the provider gives you the necessary rights to audit their performance, or at least provides independent attestation reports, such as those from the CSA Star Registry, to prove they meet the promised standards without requiring an intrusive on-site audit. Finally, incorporate the principles of continuous auditing to monitor these service commitments over time. A static review of a contract at the time of procurement is insufficient for modern cloud workloads that evolve through continuous integration and deployment. You need to establish a feedback loop where you verify that the performance metrics reported by the provider reflect your own experience of the service. This involves using automated monitoring tools to track latency and availability from your perspective, comparing that telemetry against the provider's official reports. If you consistently find a deviation, you've identified a discrepancy that requires further investigation and potential remediation. Evaluating an SLA is therefore an ongoing activity, not a once-a-year document check. By applying this level of diligence, you provide the objective assurance that the organization is not relying on hollow promises, but on verified service delivery that supports your enterprise strategy. See you in the next lecture. Welcome back. Today we are going to explore the critical components of cloud contract analysis. When we approach the audit of a cloud service agreement, we must move beyond the standard legal boilerplate to identify where the actual operational risks reside for our organization. The contract serves as the foundation for the shared responsibility model, specifically defining the boundary between the service provider's security obligations and the tenant's requirements. A primary concern during this legal and administrative review is the identification of hidden liabilities that often remain obscured in standard terms of service. You should look specifically for clauses that limit the provider's liability to such an extent that recovering damages after a major data breach becomes practically impossible. Another critical area involves the right to audit clause, which is frequently the most contentious part of the negotiation process. If the contract explicitly prohibits independent third-party assessments, your ability to provide reasonable assurance to stakeholders or regulators is significantly diminished. We must verify whether the contract permits the use of independent attestation reports, such as ISO 27001 or SOC 2 Type 2, in lieu of physical access to data centers. Exit strategies and data extraction clauses are perhaps the most vital technical components that require an auditor's scrutiny before a contract is finalized. You need to ensure that the provider commits, in writing, to the timely migration and retrieval of data in a non-proprietary standard format upon termination of the agreement. Without clear language regarding data portability, the organization risks significant vendor lock-in, which effectively increases the cost and difficulty of switching providers. We should also audit the termination conditions to see if they address the immediate secure deletion or overwriting of data resident on multi-tenant hardware. It is not enough for a provider to simply state they will stop charging for the service. They must provide evidence of sanitization processes that align with industry standards like NIST SP 800-88. An auditor must confirm that the agreement includes provisions for the provider to certify that all copies of the tenant's data have been destroyed post-termination. Investigating these lifecycle markers early prevents the common trap of organizational data remaining in ghost backups long after the cloud account is technically closed. Compliance mapping within these contracts requires that we align specific control responsibilities with the frameworks our organization has chosen, such as the CSA, CCM, or CAIQ. Many service level agreements, or SLAs, are written to optimize for uptime and availability without clearly articulating the security performance metrics that auditors rely on. For example, a contract might guarantee 4 nines of uptime, but it might remain silent on the required response time for an incident occurring within that infrastructure. We must evaluate whether the SLA includes penalties or recourse mechanisms for failures in security operations, such as delayed patching or inadequate identity and access management controls. Furthermore, consider how data sovereignty and jurisdictional requirements are addressed in the contract, especially when the provider uses a global mesh of data centers. If the legal entity providing the cloud service is headquartered in a region with weak data protection laws, or if the data can be stored in jurisdictions that do not meet your internal compliance standards, the contract is inherently flawed from a risk management perspective. Finally, we must integrate our audit of these legal instruments with the technical reality of our hybrid or multi-cloud architecture. Audit rigor in a virtualized, dynamic environment means that we cannot rely solely on static paper reviews of an old legal contract. We must look for requirements within the contract that mandate the provider to share logs, provide access to security orchestration APIs, or participate in joint threat intelligence exchanges. If the contract does not specifically allow for the evaluation of microservices or container-based workloads, you may find yourself legally blocked from performing necessary security validation during a high-stakes investigation. Evaluating the effectiveness of controls depends on having the legal right to monitor the provider's performance against their documented security policies. By aligning our audit methodology with the specific language of the contract, we ensure that our oversight is not just performative, but deeply anchored in the provider's contractual duties. This approach creates a transparent partnership rather than a blind reliance on a third-party vendor whose internal operations remain opaque. I will see you in the next lecture. Welcome back. Today we transition from static audit methodologies into the dynamic realm of continuous assurance frameworks. When we shift our perspective from periodic point-in-time audits to continuous assurance, we are essentially moving from a snapshot-based mindset to a state-based monitoring model. Traditional auditing often relies on the retrospective review of historical data, which is fundamentally incompatible with the fluid nature of cloud-native infrastructure. In a continuous assurance model, the goal is to integrate automated security posture management tools, or CSPM, directly into the fabric of your environment. This practice allows us to dynamically evaluate controls against established governance policies in real time. By automating the comparison of current system configurations against the cloud controls matrix, we can identify drift the moment it occurs rather than waiting for an annual compliance check. This transition requires a fundamental shift in how we gather evidence, as the evidence itself is now generated and logged by automated agents rather than human-curated spreadsheets. As auditors, our role evolves from manual verification to auditing the configuration and output of the tools that enforce these policies. Building a sustainable framework requires a deep understanding of the shared responsibility model as it pertains to specific service models. You must delineate clearly between the provider's obligation to secure the underlying hypervisor or physical infrastructure and the tenant's duty to configure the virtual environment and data access policies correctly. Your framework should encompass technical, operational, and administrative controls, mapping directly to the CSA, CCM, or CAIQ frameworks. When evaluating the effectiveness of these controls, you need to focus on automated validation of cryptographic implementation and data sovereignty. It is not enough to simply confirm that encryption is enabled. You must verify key management strategies, including the rotation lifecycle and accessibility policies for master keys. Any continuous assurance plan must also account for incident response and forensics in a distributed system, ensuring that sufficient telemetry is preserved to reconstruct events without relying on transient, ephemeral logs that might be wiped during a restart. The complexity increases significantly when we introduce hybrid and multi-cloud environments, as the control plane is no longer singular or unified. Your auditing framework must account for the lack of global parity across different providers, necessitating an abstraction layer in your monitoring strategy. This is where the concept of third-party supply chain risk becomes paramount, especially when services are built upon a chain of microservices and serverless functions orchestrated by containers. Reviewing vendor-independent attestation reports remains a core requirement, but it must be supplemented by independent validation of your own specific environment settings. You are tasked with ensuring that internal governance policies are consistently applied across heterogeneous environments, which often requires a standardized policy as code approach. This automated approach to policy enforcement serves as the backbone of your continuous assurance framework, transforming subjective assessments into objective data points. By formalizing this monitoring through service-level agreements, you can hold both internal teams and external providers accountable for the state of the security posture. Ultimately, this maturity level enables an organization to provide evidence of compliance at any given moment, significantly reducing the cognitive load during traditional audits. By focusing on remediation tracking and planning, the framework ensures that identified deficiencies are not only logged, but are addressed through an established workflow. The integration of vulnerability management tools into this loop closes the gap between risk identification and system hardening. Maintaining objective independence in this context means your audit must be based on verifiable data generated by tools that you have scrutinized for their own reliability and accuracy. We are effectively engineering auditability into the system architecture itself. This approach shifts the culture from compliance being a deterrent to innovation, to compliance being a supportive, automated safety net that enables faster, more secure deployments. When the architecture is validated through continuous assessment, the risk of configuration errors, the leading cause of cloud data breaches, is statistically lowered. I will see you in the next lecture. Welcome back to our exploration of cloud auditing controls. In this lesson, we will focus on evaluating data encryption mechanisms as they apply to cloud-hosted environments. When we audit encryption, we often fall into the trap of assuming that simply enabling a feature satisfies the security requirement. An effective audit must move beyond the claim that data is encrypted to verifying the implementation of that encryption at rest and in transit. For data at rest, we must examine the cipher suites being utilized by the storage service, comparing them against industry-standard benchmarks like those recommended by NIST or specified within the CSA Cloud Controls Matrix. It is important to confirm that the service providers are using strong algorithms, such as AES 256, rather than outdated implementations that might be susceptible to known vulnerabilities. We must ask whether the underlying storage abstraction provides transparent encryption or if it requires specific configuration by the tenant. These technical controls serve as the bedrock of our assessment, but they are meaningless if the cryptographic keys are improperly handled or managed. Evaluating data in transit requires a shift in our perspective toward network architecture and protocol negotiation. We are looking for evidence that transport security such as TLS 1.2 or 1.3 is strictly enforced for all service endpoints and internal service-to-service communication. Many cloud environments allow for legacy protocol support, which can lead to downgrade attacks, so an auditor must verify that these are explicitly disabled at the load balancer or ingress controller level. We also need to assess the certificate management process, ensuring that certificates are not only valid, but issued by a trusted, monitored authority. When reviewing the configuration of private endpoints, we look for evidence that traffic is forced through encrypted tunnels, especially when traversing across different cloud regions or between hybrid environments. If the environment relies on third-party integrations, the validation extends to whether the encryption handshake is consistent across those external boundaries. Operational control over encryption cannot be separated from the broader strategy of identity and access management. Many organizations fail their audits because encryption is correctly configured, yet authorized access to the decryption keys is overly permissive. We must examine the policies attached to key management services to ensure the principle of least privilege is strictly applied. This involves auditing the segregation of duties between the administrators who manage the infrastructure and the security officers who have the permissions to access or rotate cryptographic keys. By cross-referencing activity logs with these access policies, we can determine if there are unauthorized attempts to access sensitive data stores. A secure system is not just one that uses strong mathematics, but one where the lifecycle of the key itself is governed by transparent, immutable auditing processes that notify stakeholders of any anomalies in usage patterns. Finally, we must align our evaluation with the shared responsibility model by identifying where the cloud provider's attestation reports end and the tenant's configuration begins. Vendor-provided SOC2 or ISO reports often certify the hardware security modules and the integrity of the underlying encryption platform, but they do not prove that you configured your specific virtual instances correctly. Our audit methodology must focus on gathering evidence through programmatic means, such as reviewing infrastructure as code templates, or utilizing cloud-native configuration assessment tools to detect drifts in compliance. We look for continuous validation of these settings, acknowledging that in dynamic environments like microservices or containerized workloads, a point-in-time assessment is rarely sufficient. By checking for evidence of encryption implementation alongside a review of service-level agreements regarding data protection, we ensure that the business strategy regarding information security remains resilient, compliant, and defensible against evolving unauthorized access threats. I will see you in the next lecture. Welcome back to our journey through the complexities of cloud auditing. In this lesson, we will pivot our focus toward the critical domain of cryptographic key management systems and how they function within the cloud audit sphere. When we approach the audit of a centralized cryptographic key management system, or KMS, we are essentially looking at the heartbeat of data privacy in the cloud. As auditors, our primary objective is to verify that keys are protected with the same intensity as the data they are designed to secure. We need to examine how these keys are generated, ensuring that the entropy sources are robust enough to resist cryptanalytic attacks. Furthermore, rotation policies must be evaluated not just for existence, but for their adherence to defined life cycles that minimize the blast radius if a key is compromised. Revocation processes require equally rigorous scrutiny because an inefficient revocation mechanism leaves an organization vulnerable even after a breach has been identified. It is not enough to rely on the provider's interface. We must look for evidence of how these policies are enforced across the entire backend infrastructure for the tenant. A significant portion of our assessment involves understanding the integration between the cloud-native KMS and hardware security modules, or HSMs. Secure enclaves and FIPS 140-2 or 140-3 validated HSMs provide the hardware-level trust necessary for high-stakes cryptographic operations. During an audit, you should evaluate whether the keys are stored in a dedicated, tamper-resistant environment that prevents extraction by the cloud provider's personnel. This is where the shared responsibility model becomes concrete. While the cloud provider manages the physical HSM hardware, the tenant is responsible for configuring access policies and auditing the usage logs. Check for the delineation of duties, ensuring that the roles managing the key rotation policies are segregated from the roles that have the capability to use the underlying cryptographic keys. This separation of duties is a fundamental control that, if missing, creates an immediate deficiency in your findings. Technical, operational, and administrative controls must be examined through the lens of frameworks such as the CSA, CCM, and CAIQ. An auditor must verify that administrative access to the KMS is restricted and protected by robust identity and access management policies, such as multi-factor authentication and just-in-time access. From a technical perspective, we analyze the API calls against the KMS to ensure every request is authorized and logged with sufficient detail for forensic reconstruction. We are looking for a continuous audit trail that captures not only who accessed which key, but also when and for what purpose that key was utilized in a cryptographic operation. If the environment supports automated assessment, verify that these tools have read-only access and cannot influence the actual state of the key policy, as this would violate the independence of the audit itself. Data sovereignty and jurisdictional requirements add another layer of complexity to our audit plan. When keys are managed across hybrid or multi-cloud architectures, we need to ensure that the keys are physically stored or logically locked within jurisdictions that align with the organization's regulatory obligations. I have often seen situations where data is stored in one region while the encryption keys reside in a jurisdiction with weaker privacy protections, effectively undermining the tenant's security strategy. You must validate the mapping of your key management controls to the specific business and IT strategies defined by the organization. This involves assessing the risk mitigation strategies for third-party supply chain risks, especially when integrated third-party services rely on the same KMS for data decryption purposes. For effective deficiency reporting and remediation tracking, auditors should be looking for systemic gaps rather than just individual misconfigurations. When we report a finding, it should clearly state the control objective that was not met and provide evidence gathered through our assessment of the KMS logs and policy documentation. This process is iterative. If a deficiency is identified, we assess the timeline for remediation and the potential impact on data confidentiality. Reporting needs to be concise, pinning the failure to specific policy deviations or architectural oversights in the key hierarchy. By aligning our assessment with the resilience requirements of the organization, we can provide a realistic evaluation of the cryptographic posture that supports both compliance and operational continuity. See you in the next lecture. Hello, and welcome back as we explore the complexities of cryptographic management in modern cloud environments. In this session, we will focus on Bring Your Own Key and the broader implications of key ownership and control. Bring Your Own Key, or BYOK, is a paradigm designed to bridge the gap between cloud provider convenience and tenant-controlled security requirements. In a standard cloud deployment, the cloud service provider manages the cryptographic keys by default, which simplifies operations but creates a dependency on that provider's internal security controls. When an organization moves to BYOK, they generate their own keys on-premises or within a hardware security module they control, then export those keys to the cloud provider's key management service. The primary advantage here is that the tenant retains ownership of the root material, allowing for a centralized key lifecycle process that spans both on-premises data centers and cloud service environments. However, this transition is not without operational hurdles, as it mandates a robust synchronization between legal retention requirements and technical implementation, specifically concerning how keys are imported and managed. Auditors must verify that the transfer mechanism itself is secure, using wrapping keys and strictly defined transport protocols to prevent the exposure of plaintext key material. Furthermore, we must assess whether the provider's implementation of an imported key mirrors the capabilities of a native key, as functionality disparities can lead to degraded performance or failed compliance audits. The logical extension of BYOA is Keep Your Own Key, or KYOK, which often involves the use of cloud-based hardware security modules where the tenant maintains exclusive access. While BYOK provides a level of comfort regarding ownership, KYOK represents a more rigorous control objective, effectively prohibiting the cloud provider from accessing the keys even if they were compelled to do so by a third party. When evaluating these models, an auditor must look beyond the mere existence of the policy and scrutinize the actual technical controls governing access to the key management interface. We need to audit the identity and access management configurations that protect these sensitive operations, ensuring that the principle of least privilege is applied to those individuals who can manage key rotation, revocation, and deletion. From a data sovereignty perspective, understanding where the keys are stored, handled, and used is critical because the location of the key material can effectively dictate the jurisdictional boundaries of the data it encrypts. If a cloud service provider manages the keys in a region that conflicts with the organization's data residency requirements, the organization remains at risk despite the use of encryption. The shift toward these models necessitates a deep dive into the shared responsibility model as it pertains strictly to cryptographic operations. The provider is typically responsible for the availability and integrity of the key management service underlying the infrastructure, but the tenant is responsible for the policy, usage, and rotation of the keys themselves. This is where many companies fail during an audit, as they assume that moving their own key into the cloud equates to total security, ignoring the fact that the underlying service could still be misconfigured. When assessing the effectiveness of these controls, you must confirm that there is formal documentation in place that details the incident response procedures specifically for key compromise. If a key is accidentally deleted or corrupted, the data it protects may become permanently inaccessible, making the disaster recovery plan for keys just as important as the data backups themselves. I look for evidence of automated monitoring that alerts the security team to unauthorized attempts to access or modify key policies. You should treat key management as a critical component of the overall security architecture rather than a check-the-box regulatory exercise. Maintaining objective independence while auditing these systems requires a technical familiarity with how cloud providers interface with external hardware security modules. We must verify that the audit trails for key usage are comprehensive, immutable, and properly exported to a centralized security information and event management system for long-term retention. These logs must capture not only successes, but also every failure, as patterns of failed attempts often constitute an early warning sign of an impending internal or external threat. In the context of microservices and containerized environments, the challenge is amplified because individual services may dynamically request access to keys to perform decryption operations. We should assess whether the identity assigned to the container or the serverless function is granular enough to prevent lateral movement if that workload is compromised. Finally, remember that compliance validation for BYOK and KYOK involves reviewing the provider's independent attestation reports and ensuring that the specific controls mentioned in our scope align with their SOC and ISO audit results. By focusing on these granular technical and operational elements, you will be well positioned to provide a comprehensive evaluation of the organization's cryptographic posture. I will see you in the next lecture. Welcome to this session on cloud logging mechanisms, a critical component for maintaining visibility and accountability in any distributed architecture. When we talk about cloud logging, we are effectively talking about the digital heartbeat of your infrastructure. In an on-premises world, logs were often static files residing on local disks that an auditor could physically verify. Moving to a cloud environment abstracting the physical layer, we must instead rely on structured, centralized, and immutable log streams. The primary objective is to maintain an audit trail that is not only comprehensive, but also resilient against unauthorized alteration or deletion. Without proper mechanisms for log aggregation, you essentially operate in the dark, unable to piece together the sequence of events that led to a security incident or a configuration drift. We look for technical controls that enforce separation of duties, ensuring that the individuals managing the infrastructure cannot simultaneously modify or delete the audit logs themselves. Log aggregation serves as the foundational layer for integrating your cloud environment with a security information and event management system, or SIEM. As you transition from logs to actionable insights, you need to ensure that the data being ingested is consistent and normalized. This involves leveraging cloud-native tools that provide built-in connectors for services like identity management, object storage, and compute instances. A common trap is assuming that gathering these logs is enough. But effective auditing requires you to evaluate the ingestion pipeline for latency and completeness. If an attacker gains administrative privileges, one of the first things they will attempt to do is wipe their tracks by purging log history. Consequently, you must verify that your logging architecture uses write-once-read many storage policies to ensure immutability, which acts as a deterrent and a recovery mechanism in forensic investigations. When assessing the effectiveness of these mechanisms, you should align your evaluation criteria with the CSA Cloud Control Matrix, or CCM. Administrative controls are just as vital as technical ones, specifically regarding who has the permission to configure log retention policies. An auditor must scrutinize the lifecycle of a log entry, from the moment it is generated by a cloud service to its eventual archiving or deletion. You need to verify that retention durations are compliant with legal and regulatory requirements, such as those found in data sovereignty or privacy mandates. In hybrid or multi-cloud environments, ensure that the logging schema is standardized across different vendors, preventing the creation of disjointed silos that complicate incident response efforts. This mapping of control objectives to technical implementation is the cornerstone of validating that your cloud service provider is meeting their obligations. Consider the reality of dynamic, virtualized environments where assets might only exist for minutes, such as short-lived container instances or serverless functions. These ephemeral assets present a unique challenge because their lifecycle often ends before a manual audit can take place. Your strategy must shift from point-in-time reviews to continuous auditing, where log data is used in real time to trigger alerts on anomalous behavior. Examine how the cloud provider delivers these telemetry streams, whether through programmatic APIs or integrated dashboarding tools, and evaluate their reliance. During an audit, you should seek evidence of successful log integrity checks, where cryptographic hashing is used to prove that the logs have not been tampered with since their inception. This provides the objective independence needed to attest to the security of the underlying cloud platform. In the context of incident response and forensics, The presence of comprehensive logs determines the speed and accuracy of your investigation. You are assessing whether the logged information contains sufficient contextual data, such as source IP addresses, user identity tokens, and the specific API calls requested. If you are conducting a forensic analysis, you will need to reconstruct the attacker's progression, which is impossible without a unified view of these activities. Remember that the shared responsibility model places the burden of log monitoring and analysis firmly on the tenant, while the provider is generally responsible for the underlying infrastructure logs. Failure to bridge this gap usually results in a significant audit finding, as it exposes the organization to blind spots that can be exploited for data exfiltration or service disruption. See you in the next lecture. Welcome back. In this session, we will examine the mechanisms of cloud monitoring and alerting to ensure your audit assessments remain robust and evidence-based. When we approach the audit of cloud monitoring infrastructures, we are fundamentally attempting to verify the visibility and responsiveness of a platform that is inherently abstract and distributed. An auditor must move beyond merely checking if logs are being generated and instead focus on the efficacy of the heuristics and thresholds that trigger alarms. In a traditional on-premises data center, a monitoring tool might watch CPU utilization or memory pressure on physical hosts, but in the cloud, these metrics are often abstracted away by the provider. You must evaluate whether the monitoring solution correctly interprets the telemetry provided by cloud APIs and whether the configured thresholds for anomaly detection are actually aligned with business performance baselines. If these thresholds are too loose, you risk missing security incidents. If they are too tight, you create a torrent of false positives that leads to alert fatigue, potentially blinding your operations teams to genuine threats. Effective evaluation of these systems requires an understanding of how alarm routing and correlation function across heterogeneous, distributed environments. Modern cloud architectures often rely on microservices that emit logs to different locations, such as centralized object storage or specialized log management services. As an auditor, you need to verify that these individual signals are properly correlated into meaningful events rather than remaining as isolated data points. Ask yourself if the alerting infrastructure is capable of linking an unusual identity access attempt with a sudden change in database configuration, as this correlation is often the only way to detect a multi-stage attack. You should examine the administrative controls surrounding the alert pipeline, ensuring that only authorized personnel can modify notification rules or suppression lists. If a developer can silently disable alerts for a specific production workload, the integrity of your entire monitoring control set evaporates. Operational control assessment should also focus on how current monitoring practices support your broader incident response and forensic obligations. When a security event occurs, the quality of your stored logs and the timeliness of your alerts determine the success of the subsequent investigation. Verify that the monitoring implementation encompasses both infrastructural metrics and application-level events, providing enough context for a post-mortem analysis. You must also validate that the monitoring tools operate within the constraints of the shared responsibility model. While the cloud provider monitors their underlying physical infrastructure and virtualization layer, you are responsible for monitoring the logic within your tenant environment. A common audit finding is the gap between network-level monitoring at the provider layer and the visibility required at the application layer, which often requires custom instrumentation or agent-based solutions. Compliance and risk mitigation are inextricably linked to the monitoring lifecycle, especially when dealing with data sovereignty and jurisdictional requirements. Your assessment should confirm that log data containing sensitive metadata is not being exported to a region that violates local data protection laws. During your audit, request evidence of how the provider handles monitoring data during regional failover events, as data sovereignty obligations often apply even to metadata stored in centralized monitoring consoles. Furthermore, review how vulnerability management data is integrated into the alerting framework. An alert for an unauthorized configuration change should ideally be cross-referenced with your vulnerability management database to determine if the affected asset is already known to be at risk. This integration demonstrates a mature operational capability and helps prioritize mitigation efforts based on true risk rather than just raw volume. Finally, consider the audit trail of the monitoring system itself as a necessary control for verifying independent attestation. Just as you scrutinize the logs of your application, You must scrutinize the logs of the monitoring platform to ensure no unauthorized tampering with incident history has occurred. Ensure that your reporting processes include the periodic validation of these monitoring tools against the documented security objectives within the CSA Cloud Controls Matrix. By evaluating the continuous assurance capabilities of the environment, you provide the organization with a verifiable way to demonstrate compliance, which is essential for audit rigor in a dynamic, virtualized ecosystem. Your report must clearly delineate between the effectiveness of the technical implementation and the administrative maturity of the incident management processes that consume these alerts. See you in the next session. Welcome back to our discussion on cloud auditing. Today, we are focusing on the specifics of auditing cloud incident response capabilities within distributed environments. Cloud incident response represents a significant departure from traditional on-premises recovery procedures due to the reliance on a shared responsibility model. When an organization moves into the cloud, the division of labor between the cloud service provider and the tenant becomes the primary point of failure during a security breach. As an auditor, your first task is to verify whether the service level agreement clearly defines the boundary of responsibility for incident detection and containment. In a standard IaaS model, the provider typically manages the physical infrastructure and hypervisor, while the tenant remains responsible for the guest operating system and applications. If an incident affects the underlying fabric provided by the vendor, the tenant may have zero visibility into the root cause, making forensic data acquisition nearly impossible without provider collaboration. You must scrutinize the contract to see if legal clauses exist that mandate the provider to assist in forensic investigations when requested by the tenant. Without these formal protocols, the tenant is often left without the logs necessary to reconstruct the attack timeline. To evaluate the effectiveness of these responses, we must look at how automated containment strategies are implemented. Modern cloud environments utilize orchestration tools that can dynamically isolate affected instances or revoke identity credentials to stop lateral movement. An effective audit involves checking if these automated triggers are configured according to predefined risk thresholds rather than arbitrary rules. For example, if a virtual machine begins exhibiting signs of command and control traffic, does the automated system quarantine that resource while maintaining state for later analysis? If the automated containment is too aggressive, it risks disrupting business continuity, whereas a passive system might allow the attacker to compromise data integrity. So the auditor must look for the balance. You should evaluate documentation regarding how the organization validates their incident response playbooks under simulated stress conditions to ensure they function as designed. Furthermore, verify whether the incident response team has been granted the necessary granular permissions, typically managed through identity and access management roles, to act within the containerized or virtualized environment without requiring manual intervention during the crisis. Forensic data acquisition in the cloud presents unique technical challenges that require a shift in methodology from traditional disk imaging techniques. Because multi-tenant architectures prevent you from accessing physical drives, you must rely on ephemeral data, cloud provider logs, and snapshots taken at the time of the incident. Auditing these capabilities requires you to confirm that the organization is backing up logs to an immutable and geographically separate storage account. If logs are stored on the same infrastructure that has been potentially compromised, an attacker can simply delete the audit trail to hide their activities. You must check if the organization is using centralized logging services and if those logs are protected by cryptographic integrity checks. In addition to technical controls, you need to verify the administrative side, specifically regarding the existence and testing of the incident response plan. Is there a clear communication path between the Security Operations Center and the cloud service provider's emergency contact desk? These collaborative protocols are often the difference between a minor security event and a breach that results in significant regulatory noncompliance. Finally, consider how the auditing process itself ensures consistency during these volatile periods. Your audit scope must include a review of how the organization tracks incident remediation and whether they provide post-incident reports to relevant stakeholders. This process should map back to the shared responsibility model, ensuring that the cloud service provider's commitments are not just theoretical, but actionable during an actual security breach. Be wary of organizations that rely entirely on the provider to handle incident response without performing their own verification of the controls. You are looking for evidence of independent assessment, such as reviewable SOC reports or other independent attestation reports that confirm the provider's capability to support your forensics team. If the organization cannot demonstrate that they have validated these links between their own internal security team and the vendor's response framework, they possess a significant control deficiency. This gap creates a risk not just to data security, but to the regulatory compliance posture of the entire organization. I look forward to discussing our next topic in the following session. Welcome back to our exploration of cloud auditing, where we now turn our attention to the critical task of auditing API security. Application programming interfaces serve as the digital connective tissue of modern cloud environments, making them a primary target for malicious actors. When auditing these interfaces, your objective is to move beyond high-level policy checks and into the technical implementation details that define real-world security. You must start by evaluating how authentication is handled, particularly looking for the use of modern, robust protocols like OAuth 2.0 or OpenID Connect rather than legacy methods. Check whether tokens are properly scoped, have short lifespans, and are transmitted exclusively over encrypted channels. If an application relies on static API keys, you should flag these as a significant risk unless they are subjected to stringent rotation and secure storage practices. Remember that an API that is functionally convenient but ignores transport security is essentially an open door into your cloud architecture. Rate limiting and throttling represent the next layer of defense that requires your scrutiny as an auditor. Without these controls, APIs are inherently susceptible to denial of service attacks or brute force attempts aimed at credential stuffing. You need to verify that implementation reflects a business-aligned strategy where different endpoints have appropriate thresholds based on their sensitivity and usage patterns. Inspect the configuration of the API gateway, as this is usually the point where these policies are enforced across distributed microservices. A well-configured gateway acts as a centralized enforcement point that simplifies your audit trail significantly. If you find that rate limiting is implemented inconsistently across services, this inconsistency often points to an architectural oversight that weakens the overall posture of the cloud deployment. Data validation and parameter manipulation form the backbone of input security, and you must treat them with the same rigor you would apply to traditional web application audits. Verify that the API implements strict schema validation so that only expected data formats are accepted by the backend services. Look for evidence of protection against common vulnerabilities, such as injection attacks or broken object-level authorization, which is a frequent culprit in data breaches. Even if the service provider manages the underlying infrastructure, the tenant remains responsible for the logic governing access to specific resources via API calls. If the audit shows that input filtering is performed only on the client side, then you have found a critical control failure that demands immediate remediation. Your verification should include a review of how logs capture attempts to bypass these validation routines, as this data is essential for incident response. The shared responsibility model requires a clear delineation of obligations, especially when you are evaluating the security of third-party API providers versus your own internal configurations. You must gather evidence that demonstrates how the provider fulfills its part of the security contract, often by reviewing their SOC 2 reports or their CSA CAIQ submissions. At the same time, you must audit the identity and access management configurations that you control, ensuring the principle of least privilege is applied to all service accounts. Look for evidence that cryptographic keys used to sign tokens are managed in a hardware security module or a dedicated key management service. Failing to verify the integrity of the key management lifecycle means that even the strongest tokens could be compromised by an adversary who gains access to the underlying signing material. Finally, consider the auditability of these components in a dynamic, containerized environment where services may scale or vanish based on performance demands. Your audit methodology must adapt to include continuous monitoring of API logs and automated assessment tools that keep pace with rapid deployment cycles. Review the incident response playbooks to see if they specifically address API-level threats or if they rely on generic procedures that might be insufficient for microservices environments. Reporting deficiencies must be tied back to documented risks, providing stakeholders with a clear path toward remediation and compliance. This methodical approach ensures that your audit not only checks boxes, but actually contributes to the resilience of the multi-cloud architecture. See you in the next lecture. Welcome back. In this lesson, we will focus on the practical methodologies required to audit third-party and fourth-party vendors within the complex, interconnected landscapes that define modern cloud ecosystems. When we approach the audit of a third-party vendor, we must first recognize that the fundamental tenets of the shared responsibility model do not vanish simply because a service is outsourced. Instead, your responsibility shifts from direct control to the effective management of oversight and validation. You are not auditing the infrastructure in the same way you would audit an on-premises data center, but rather you are evaluating the effectiveness of the control environment that the provider asserts is in place. This requires a transition from verifying physical cable locks or server room temperatures to examining standardized audit artifacts, such as SOC 2 Type 2 reports, CSA STAR attestations, or ISO 27001 certifications. You must develop a keen eye for assessing whether the scope of these reports truly covers the specific services your organization consumes, as a generic certification document is rarely a substitute for a targeted risk assessment. A robust vendor assessment program must rigorously distinguish between the cloud service provider and the underlying fourth-party dependencies that the provider relies upon for its own operations. This is often where many audits fail. The assumption is that the primary provider is inherently responsible for the security posture of their own upstream supply chain. In reality, you need to probe how your vendor manages their own supply chain risks, particularly concerning their choice of data centers, managed services, or specialized cloud modules. You should review their vendor risk management policy and look for evidence of how they perform their own due diligence, as their failure to secure their own fourth parties immediately translates into a security risk for your data. This is not about micromanaging their internal business processes, but about confirming that they possess a structured methodology for vetting their own vendors that aligns with your internal risk appetite and regulatory requirements. When evaluating the technical and administrative controls of a vendor, the Cloud Security Alliance's Cloud Controls Matrix, or CCM, serves as an indispensable framework. You should map the vendor's control objectives to the specific areas where they provide service, paying close attention to identity and access management, data encryption, and key management strategies. It is not enough to receive an affirmation that encryption is enabled. You must verify that the vendor manages keys in accordance with industry best practices, such as hardware security module utilization or strict separation of duties. If your organization mandates data sovereignty, you must validate that the vendor's service delivery architecture respects geographic boundaries, especially when using multi-cloud or hybrid configurations. Evidence gathering in this context involves examining granular artifacts like configuration change logs, penetration test summaries, and documented incident response procedures that demonstrate the vendor's ability to operate securely in your specific regulatory context. Continuous auditing and monitoring of service-level agreements constitute the operational heart of long-term vendor risk management. You cannot simply perform a point-in-time assessment during the contract initiation phase and assume that the security posture remains static for the duration of the engagement. Instead, establish a cadence for reviewing the vendor's performance against their committed metrics, including uptime, incident reporting latency, and vulnerability management turnaround times. Look for transparency in how the vendor communicates security incidents, as a partner who hides a breach or refuses to provide forensic logs is a liability regardless of their initial security scores. You should also demand access to, or summaries of, the vendor's vulnerability scanning results and evidence of remedial actions taken when high-risk vulnerabilities are identified. Finally, ensure your audit process culminates in a clear, actionable report that categorizes identified deficiencies by severity and potential business impact. This reporting phase is essential for remediation tracking, where both you and the provider agree on a timeline for addressing identified control gaps. If the vendor cannot provide adequate evidence for specific control areas, you may need to implement compensatory controls on your side to mitigate the risk effectively. This entire process necessitates that you maintain objective independence throughout the engagement, especially when dealing with major cloud providers that may be resistant to traditional audit requests. By focusing your audit rigor on the efficacy of the demonstrated controls rather than on the vendor's marketing materials, you establish a resilient hybrid or multi-cloud environment that is far better prepared to withstand supply chain disruptions and security threats in the long term. See you in the next lecture. Welcome back. Today, we address the critical landscape of supply chain attack vectors in modern cloud environments, focusing on how we audit these dependencies. In a cloud-native ecosystem, the software supply chain has expanded far beyond the traditional vendor procurement model of the past. When your organization consumes a cloud service or integrates a third-party library, you are essentially importing code and operational trust into your own delivery pipeline. A supply chain attack vector manifests when a malicious actor compromises these upstream components, such as open-source libraries, container-based images, or infrastructure as code templates to inject vulnerabilities or backdoors. From an auditing perspective, simply verifying the vendor's security posture is no longer sufficient because the threat often originates much further down the chain. You must evaluate how the development team manages these dependencies, specifically looking for evidence of software composition analysis tools being integrated into the build process. If an application pulls a component from a public repository without validation, the provenance of that code is unknown, creating a blind spot that auditors must address. To assess these risks, we apply the CSA Cloud Controls Matrix, or CCM, to determine if the provider or the tenant has adequate visibility into third-party code integrity. You need to investigate the control objectives surrounding code signing and hashing, which ensure that the software in production is identical to the software that underwent security testing. When evaluating a service provider, request their attestation reports, such as a SOC 2 Type 2, but look specifically for the section addressing the security of their own software development lifecycle. In the context of microservices, a frequent point of failure is a compromised CI/CD pipeline, where an attacker modifies the build process itself to include malicious code during the compilation phase. Your audit should focus on whether the organization enforces strict access control over build servers and whether they maintain a strictly immutable audit log of every change made to the repository. Administrative controls here involve reviewing the policies that govern how new dependencies are introduced, vetted, and approved for use in production environments. The complexity increases when we consider the shared responsibility model, as the cloud provider secures the infrastructure, but the customer retains responsibility for the security of the application code and its dependencies. If you are using containerized workloads, you must examine how your organization manages the base images stored in internal registries. A common vulnerability occurs when developers use unpatched or deprecated images that are pulled from public repositories without a local caching strategy or vulnerability scanning. As an auditor, you should verify that there is a documented process for periodically rescanning existing artifacts for newly discovered vulnerabilities, as the threat profile of a library changes continuously after its deployment. If a vulnerability is found in a widespread library, like a logging utility, the organization must be able to inventory every single service that incorporates that library within minutes rather than days. This requirement maps directly to the operational maturity required within the CCAK framework, demonstrating that technical rigor is paired with effective risk management monitoring. Furthermore, we must address the specific mechanics of data protection and how a supply chain compromise affects the privacy of information. If a third-party library is compromised and contains a data exfiltration module, all the encryption in the world might be insufficient if the attacker gains access to the decrypted memory space or the API keys used by the application. Therefore, auditing your cryptographic key management strategy becomes an essential component of assessing supply chain resilience. You need to confirm that applications are using secrets management services rather than hard-coded credentials, as hard-coded keys are a primary target for malicious dependencies once they gain execution context. When conducting your audit, verify the effectiveness of these controls by requesting evidence of revocation and rotation of keys after any significant incident or policy change. By requiring this level of objective independence, you ensure that the organization does not simply rely on the integrity of their vendors, but instead builds a defense-in-depth strategy that assumes external libraries could be compromised at any point. See you in the next lecture. Hello, and welcome back to our deep dive into the nuances of modern auditing. Today, we explore the intricate landscape of hybrid cloud deployments, a topic that sits at the intersection of traditional infrastructure and agile cloud services. When we approach a hybrid cloud deployment, we are essentially looking at the seams between disparate environments. It is not just about individual components, but how they interact across a chasm of different management planes. The auditor must remain cognizant that security controls often lose their uniformity when stretched from an on-premises data center to a public cloud provider. Your role is to evaluate whether the network interconnection, be it VPN tunnels, dedicated leased lines, or direct interconnects, possesses the necessary encryption and robust authentication to prevent unauthorized transit access. You must look for consistency in the security policy enforcement, as the heterogeneous nature of the control planes often leads to configuration drift. A policy might state that all outgoing traffic must be inspected, but if the local firewall configuration and the cloud security group rules don't mirror this intent, your control efficacy drops significantly. We define the audit scope here by observing how the boundary between trusted and untrusted is managed, regardless of where the physical or virtual assets reside. Identity federation stands as the central nervous system of any successful hybrid architecture. Without a unified identity provider, you inevitably end up with fragmented user directories that become a nightmare for granular access control and lifecycle management. When auditing this, ask how the organization ensures that a user's permissions on-premises are accurately mapped and restricted within the cloud environment. Are the attribute claims being passed correctly? And is there a mechanism to immediately revoke access across both environments if a security incident occurs? The complexity here is not just in the authentication protocol itself, such as SAML or OIDC, but in the implementation of the trust relationship between the identity provider and the relying party. If the mapping is loose, you invite horizontal privilege escalation, where an attacker gains a foothold in the less secured environment and uses a synchronized identity to gain elevated rights in the more sensitive one. Applying the CSA, CCM, and CAIQ frameworks helps us categorize these controls across technical, operational, and administrative domains. We must treat the hybrid reality through the lens of the shared responsibility model, which becomes significantly more complex when you are the one responsible for the connective tissue between environments. Examine the service level agreements to see if they account for the performance and security of this interconnection, or if that is left to the customer's implementation, which is often the case. Data sovereignty becomes a pressing concern here, as data often traverses borders or moves between jurisdictions unknowingly when it shifts from a static private server to a dynamic cloud container. You have to verify that data protection strategies, including encryption at rest and in transit, remain persistent across these migrations. Verify that encryption keys are managed according to a consistent lifecycle strategy rather than having disparate key stores that are not synchronized or, worse, lack a proper audit trail for key access operations. Continuous auditing practices are not merely a luxury in hybrid environments, they are a necessity for survival. Because these environments are fluid, a point-in-time audit provides very little assurance regarding the ongoing security posture. Your assessment methodology should prioritize automated tools that can inspect configurations across both environments simultaneously to identify discrepancies. Look for evidence of vulnerability management that covers not just the virtual machine instances, but also the container workloads that might be orchestrating tasks across the divide. When an incident occurs, is the forensic data consolidated? Or are you left trying to stitch together logs from a private syslog server and a cloud-native logging stream? Incident response planning must include the synchronization of these forensic capabilities to ensure that when a breach detection occurs on one side of the hybrid boundary, the response team has visibility into the lateral movement occurring on the other. Finally, ensure that your audit reporting reflects the reality of the third-party supply chain risks introduced by the cloud provider. A hybrid model does not absolve the organization of evaluating the security of the public cloud segment, regardless of the vendor's independent attestation reports like SOC 2 or ISO 27001. Review these reports to understand the limits of the provider's responsibility and align them with your local controls to find potential gaps. Mapping your audit observations back to business objectives helps stakeholders understand why a perceived technical weakness is actually a significant operational risk. By maintaining objective independence, verifying the validity of cryptographic implementations, and scrutinizing the microservices interactions across the hybrid architecture, you provide a clear roadmap for remediation. This rigor is what distinguishes a superficial check from a professional evaluation that truly hardens the organization's distributed systems. See you in our next discussion. Welcome back, everyone. Today, we are addressing one of the most critical components of cloud resilience, Evaluating and auditing disaster recovery and business continuity plans within distributed cloud environments. When we approach the audit of cloud disaster recovery and business continuity, we must fundamentally shift our mindset from traditional on-premises data center recovery to the dynamic, service-based reality of the cloud. The primary challenge here lies in the shared responsibility model, where the cloud provider manages the physical infrastructure, power, and high-level network topology, while the tenant remains entirely responsible for data architecture, backup strategies, and recovery orchestration. As an auditor, your task is to verify that the organization has clearly delineated its obligations versus those of the provider. You should scrutinize whether the business has defined objective recovery time objectives and recovery point objectives that actually align with the criticality of the specific service workflows. An RTO of 4 hours might be acceptable for a non-critical internal tool, but it would be catastrophic for a primary customer-facing payment gateway. Always look for evidence that these metrics have been validated through actual testing, rather than resting on theoretical assumptions or simple provider-level service-level agreement promises. Effective auditing of these systems requires an assessment that transcends documentation and dives into the technical implementation of multi-region failover configurations and data redundancy. You need to verify that backups are immutable, geographically separated to account for regional outages, and protected by their own distinct identity and access management policies. Many organizations mistakenly assume that the cloud provider's replication features automatically equate to a business continuity strategy. From an audit perspective, that is a dangerous fallacy because regional replication protects against infrastructure failure, but it does not protect against accidental data deletion, malicious insider threats, or logic corruption. You must demand evidence of periodic restoration tests that prove the data is not only backed up, but also functional and consistent across the secondary environment. Are the encryption keys managed in a way that allows them to be accessible and usable in the failover region? Or will a disaster recovery event result in encrypted, unreachable, and ultimately useless data? The complexity increases significantly when we introduce the requirement for addressing jurisdictional compliance and data sovereignty in a disaster recovery context. If an organization executes a failover from one region to another, they might inadvertently violate data residency regulations by moving sensitive personal information across borders during a crisis. During your audit, you must examine the geographical boundaries predefined in the failover architecture and cross-reference them with the organization's legal and regulatory obligations. This mapping exercise is crucial because, in the heat of a disaster recovery scenario, the automated failover mechanisms will not pause to check for GDPR or other regional compliance constraints. Furthermore, you should evaluate the incident response and forensics capabilities integrated into the recovery plan. Recovery is not just about bringing servers back online. It is about verifying that the environment is secure and that the triggering event is understood to prevent immediate recurrence. Operational and administrative controls are just as vital as the technology stack when auditing for cloud continuity. I often find that organizations have excellent technical redundancy, but completely lack the human-centric processes required to manage a transition to a failover site. You need to review the role-based access control configurations for the recovery orchestration tools and ensure that only authorized personnel can initiate the disaster recovery workflow. Consider the supply chain risks as well. If the organization relies on third-party services that themselves lack adequate disaster recovery capabilities, the organization's own recovery plan becomes essentially theoretical. Examine the service-level agreements to ensure that the provider's availability commitments for all critical dependencies are sufficient to meet the organization's overall RTO and RPO targets. Effective auditing requires verifying these dependencies by testing the actual recovery response rather than solely relying on quarterly vendor-supplied attestation reports, which often cover the infrastructure but ignore the tenant's implementation. Ultimately, the goal of an audit in this domain is to provide assurance that the organization, not just its provider, is prepared to function during an unexpected system failure. Focus your evidence gathering on the execution phase of the plan. Look for logs of past drills, post-mortem reports of simulated incidents, and verified procedures for reverting to the primary region once the crisis has passed. Ensure that the organization has mapped its critical business processes to the underlying microservices or container workloads. If there is a disconnect between the IT architecture and the business impact analysis, the disaster recovery plan is likely misaligned with organizational needs. A high-quality audit will highlight exactly where these communication gaps between IT strategy and business requirements exist, allowing the leadership to make informed decisions about resource allocation and risk tolerance. We are looking for proof that the cloud architecture is resilient by design rather than resilient by wishful thinking. I will see you in the next lecture. Welcome back. We are now turning our attention to the constraints surrounding penetration testing within the nuanced landscape of cloud environments. When we shift from traditional on-premises data centers to public cloud infrastructures, the fundamental nature of security testing undergoes a significant transformation. In a physical environment, the auditor or security team typically possesses full control over the network boundary and has explicit permission to test any device on the premises. In the cloud, this paradigm breaks down because the provider owns the underlying physical infrastructure, hypervisors, and often the management orchestration layer. Any attempt to perform a penetration test on these shared components would potentially disrupt services for other tenants, which effectively constitutes a denial of service attack from the provider's perspective. Consequently, legal and technical frameworks must be established before any testing activity commences to ensure that the tenant operates within the bounds of the provider's acceptable use policy. The rules of engagement, or RO, serve as the foundational contract between the tenant and the cloud service provider regarding what is permitted, where it is permitted, and when it is permitted. These documents are not merely procedural formalities, but are legally binding instruments that delineate the boundaries of authority in a multi-tenant ecosystem. You must recognize that while you have total control over the cloud-native resources you deploy, such as virtual machines, containers, or serverless functions, you do not have permission to probe the provider's proprietary software-defined networking or physical hosts. Attempting to scan the provider's control plane or attempting to move laterally into another tenant's environment is strictly prohibited and can lead to immediate account suspension. Therefore, an audit of penetration testing practices must always verify that documentation exists, confirming that these activities were authorized and scoped correctly. Another critical limitation stems from the ephemeral nature of cloud resources, which makes traditional long-term penetration testing cycles largely ineffective. If your target is an auto-scaling cluster of containers that exists for only a few hours during peak traffic, a static manual assessment will likely miss the dynamic vulnerabilities that appear during deployment. Cloud environments require a shift toward continuous vulnerability management, where automated tools scan infrastructure as code templates and active deployments in real time. Auditors need to assess whether the organization is relying solely on point-in-time penetration tests, or if they have successfully integrated these tests into a pipeline that evaluates the security posture of the workload continuously. The effectiveness of these assessments is tethered to how well the organization understands their specific slice of the shared responsibility model. Furthermore, auditors must investigate the granularity of logs maintained by the cloud service provider during these testing windows. If a penetration test reveals a potential vulnerability or an unauthorized path, the provider's shared responsibility mandate often dictates that the tenant lacks the deep-level system logs necessary for effective forensics. This creates an information asymmetry where the tenant knows something is wrong, but the root cause remains hidden within the provider's black box management layer. When reporting on the effectiveness of a client's penetration testing strategy, you must evaluate whether they have addressed these limitations by requesting independent third-party attestation reports like SOC2 or specialized bridge letters. These reports provide the necessary transparency regarding the provider's own security testing, which the tenant can then use to fill the gaps in their own audit documentation. Ultimately, the limitation is not about a lack of technical capability, but about respecting the shared architecture that enables cloud scalability. You are essentially testing the configuration of your own virtual fence, not the robustness of the cloud's foundational foundation, which remains the provider's exclusive domain. Auditing this process involves verifying that the client has clearly mapped their testing objectives to their specific business risk appetite without overstepping the provider's defined boundaries of operation. If they are conducting assessments without verifying the vendor's own compliance certifications for the underlying components, they are failing to mitigate the risks inherent in the supply chain and hybrid deployments. Your role is to ensure they maintain that careful balance between proactive security validation and strict adherence to the collaborative agreements that underpin cloud services. I look forward to seeing you in the next lecture. Welcome to the final session of our journey through the Certificate of Cloud Auditing Knowledge curriculum. We have now reached the point where we synthesize these disparate components into a cohesive professional practice. Over the duration of this course, we have systematically navigated the complexities of cloud-native environments, starting from the foundational definitions provided by NIST and progressing toward the intricate nuances of hybrid cloud resilience. We examined how the shared responsibility model fundamentally alters the traditional audit perimeter, shifting the focus from physical infrastructure ownership to logical configuration control and governance oversight. By dissecting frameworks like the Cloud Security Alliance Cloud Controls Matrix and the Consensus Assessments Initiative questionnaire, we established a rigorous baseline for assessing cloud service providers. We also explored the integration of security architectures, ranging from identity and access management perimeters to the microscopic level of container orchestration hardening and DevSecOps pipeline integrity. This transition from static audit snapshots to continuous assurance methodologies represents the current industry standard in maintaining effective oversight of distributed systems. An auditor's competency is defined by their ability to apply traditional professional rigor to virtualized and ephemeral resources without losing the essence of independent verification. When you evaluate cryptographic implementation, the audit objective remains focused on key management lifecycle and data protection, regardless of whether the underlying storage is an object store or a managed service. Throughout our discussion on specific audit scenarios, including supply chain risk and microservices architecture, we emphasized that the core requirement is to validate that control objectives are met despite the abstracted nature of the environment. You have learned that transparency is not merely a vendor promise, but a requirement manifested in service-level agreements and independent attestation reports like SOC 2 and ISO certifications. Your ability to map these external reports to specific business strategies and regulatory requirements is what separates an informed practitioner from a compliance checkbox generator. Moving forward, your success in this domain will depend on your commitment to maintaining a persistent awareness of emerging threats and the evolving nature of cloud service offerings. As organizations adopt multi-cloud strategies, the complexity of auditing will only increase. Necessitates a shift toward automated assessment tools and real-time monitoring of configuration drifts. Remember that the auditor's role is to act as a bridge between technical security teams and business stakeholders, articulating risk in terms that relate directly to organizational objectives and regulatory liabilities. While tools change, the principles of confidentiality, integrity, and availability remain the bedrock of our profession, guiding how we verify the effectiveness of controls in a dynamic cloud ecosystem. By adhering to the methodical approach we have outlined, you provide stakeholders with the objective evidence required to make informed decisions regarding their cloud footprint. See you in the next phase of your professional development.